Here we go. I can hear now. So in case you didn't notice, all the hecklers have come up front. If there are any hecklers in the back, please come forward. We'll make sure that you're all, I see, you're to spread it all out. That's all good. So welcome to 2023 Storage Developer Conference. My name is Jay Metz, if you don't know me. I'm the guy with the funny hat and the funny name. And I am the chair of the board of directors for Snia, and I am very thrilled to welcome you to yet another in-person conference. So that doesn't happen all the time. But before we begin, there's a couple things that we're going to talk about today. Obviously, we're going to talk about some of the conference events. But I do want to start off with at least a moment of respect for a dear colleague of ours who passed away earlier this year. Mark is and was and will always be a true legend for Snia. He has been part of Snia for many, 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 many years, and was a person who left his mark on many technological developments, both in the past and recently. And so his recent passing, he will be missed very sorely. Later on tonight, when we have the award ceremony, there will be a proper memorial. I do hope you stick around for celebrating the people who have worked very hard on behalf of Snia and the respective companies, and also to pay proper tribute to Mark. So just a moment to acknowledge that we did lose somebody that meant a great deal to us. So what's the word I'm looking for? Posthumous, my word. That's the first cup of coffee I've had today, so I'm working on it. Thank you to Mark. So, here. Yes, thank you. All right, so we have decided that we are going to try to take the next 25 years of Snia, and we're going to make sure that we move beyond where we have been into the new realm that we've been covering for quite a while, and that is specifically data. So as we started to go through the process of understanding what it is that Snia is and what we've been doing, data was one of those things that kept coming up over and over and over again. We don't just store data. Storage is not capacity. One of the things that I talk about inside of my own company often is that, now I work for a company that makes processors. So processors and storage, they're related, but if you talk to chip heads, they don't really think of storage as anything much more than capacity. But as you know, storage is not just capacity. Storage is a system of protecting data, it's making it secure. Storage is a way of interacting with memory and making sure that you get the correct bit back that you ask for when you ask for it. That's what storage is and all the systems that go around that. So Snia has started to take on the role of, well, we are more data-oriented than we are storage-oriented. And we are more oriented because you are more data-oriented. And that's what we're going to be celebrating in the Storage Developer Conference this time. So to put that into a visual perspective, we decided to change a couple of our branding images and really try to focus and take home the fact that storage is not just about drives. It's not just about capacity. It's about the way that we move data around, the way that we protect it, the way that we actually create the infrastructure for it, how we transport it, a lot of different ways that data actually interacts inside of technologies and ultimately at the end user's level. But I wanted to take a quick blast from the past and try to see where we've come up into this point. So I went back to the 2001 annual report, and I noticed that the technology of the day was the DVD. That was the key thing from 2001. Now remember that this annual report now can drink. It's been 21 years. But back then the technical highlights were about IP storage work. iSCSI was a big deal. The NFS RDMA technical work group had just been formed. And we had the Plug Fest for CIFS. And if Stephen Foskett is around here, I know he just cringed, but I'm actually using the word correctly. We are actually talking about CIFS in this case. And if you're an SMB guru, you know the joke that I'm trying to make here, and failing. Now, fast forward to 2007, 2008, what happened? Well, we were focusing on the new green storage initiative and the work that was being done for energy efficiency. SMIS was taking center stage, and we were doing a great deal of interoperability work on the management side. Had a protocol called XAM. I don't know if it was pronounced ZAM or not, because I haven't heard about, is it ZAM? ZAM, really? Okay. I haven't heard much about the extensible access method for quite a while, so I wasn't even sure. And then we had a bunch of other common technologies that we've kind of taken for granted over this time, but at one point in time they were new, and these were all promoted very heavily. Now some things haven't really changed. So we had a lot of predictions back in 2007, and some of them actually are correct. So even though the predictions of Fibre Channel's death were somewhat premature, even in 2007, those predictions have come true. And yes, we do have Fibre Channel sessions this time around, and I highly encourage you to go see what's going on in the new physical layer work that's going on in Fibre Channel. So we have been making constant progress, but at the same time, we've managed to stay true to our roots. So the agenda for today is going to be a keynote special day. A lot of keynotes that people have come up to me and said that they're going to be really, really looking forward to and good. I'm particularly interested in both the next one about software and enabled flash, as well as the one in space. Hey, I'm a space junkie. I'll go ahead and watch that one too. Obviously, it's not the only keynotes, but those are the next two on the list, and I'm looking forward to those. We've got the hands-on lab for the Swordfish, the new management structure that is the replacement for SMIS. Or shall I say, I don't know if evolution is probably the right word. Evolution works. And then we have the breakout sessions. Later on this evening, we've got the SDC networking reception. Really quickly, at the Flash Memory Summit, we had 3 winners for the technology. Sean, was it Technology of the Year? Is that what it was? Yeah. Yep. And so one of the things that's really kind of important is that each of those different technologies have dozens of people who've been working on computational storage, SDXI, Swordfish. This is not just individual efforts, and the people who have been behind the scenes really do deserve the recognition. So I hope you'll join us for the reception tonight to pay honor to those people who have really gone above and beyond the call of duty for this. And then we're going to have Birds of a Feather sessions, which I'll get to in a second. The SMB Interoperability Lab, note that's not the CIFS Interoperability Lab. The SMB Interoperability Lab, where several vendors are coming together to test and identify interoperability, connectivity, and compatibility with SMB. I want to thank Microsoft for presenting and sponsoring that PlugFest, that Interoperability Lab, excuse me. And then today we've got the keynotes. I told you a little bit about the software-enabled flash and the storage in space. We also have the question that's being asked about SSDs with CXL and whether or not they are a smart idea, wise idea, or not. I have my own opinions. I'm sure you do too. There's probably a good 60, 70 people in the room, and there's equally about 140 different opinions on that one. So. And then finally, we're going to talk about carbon measurement and reduction and trying to get some more information about green energy. Later on tonight, we've got the Birds of a Feather meetings. And I was wondering about this, like, how do you go through 5 slides of schedule? Is it really that easy to do? And the answer is no, it's really not. So I'm just going to go ahead. I'm not going to read what's going on here, but the Birds of a Feather are very successful. I'm told last night that at least one of the sessions went long because people were really enthusiastic about it. If you've never been to a Birds of a Feather session, I highly recommend that you try it. So a major thanks to our sponsors. Obviously, without them, this could not be possible. And one of the things that I'd like to point out and mention, and I got a little bit of time, one of the things I'd like to point out and mention is that as we've been moving forward with the content and happening since I joined Snia back in 2014, so each year the content has gotten better. We've actually had more content of more quality. And I've been very thrilled by the fact that as we've been moving forward with these different kinds of technologies, we've got everything from computational storage to transports. We've got DNA storage. We got your capacity. We got your management. We got everything you want. Just come over here. We get it. No problem. But as we've been doing this, as we've been starting to go through, we've been attracting more and more attention from other organizations and other areas of interest, other disciplines. Let's put it that way. Last year we had really fascinating conversations in the keynotes, in particular with high-performance computing. CXL was a major part of this. And only a few years ago, people would never have thought that storage and memory were one and the same. And now we've been on a collision course between those two different technologies for a long time, where they're actually blending quite well and quite nicely now. So it's very easy to see that a lot of these conversations are starting to broaden out to include other organizations and other other types of companies who may not normally think about using a storage developer conference to show off what they've been doing. But as you can see from our sponsors this year, we've got quite an eclectic group of companies and organizations. And we're very proud to welcome them to the storage developer family, and we hope that we'll continue to do so in the future. Now, obviously what we like to do is we want to make sure that everybody here is getting the most out of their time here. So without having any further ado, I'd like to go ahead and introduce our next keynote speakers. And, yep. So, is it set up? Nope, just me. Okay. So I'd like to introduce Eric Reese, Senior VP of Kioxia, and Scott Stetzer, who is the VP of Kioxia America, to come and talk about the software-enabled flash. So essentially, how many people know what SEF is all about? Ooh. I was like, I hope the speakers do. It's going to be a very short conversation. All right, so the idea is that it's a combination of hardware and software, open source software, to enable the ability to interact with Flash at a much more open level. Where is, okay, there we go. So welcome, and you're all mic'd up. That's good to hear.
Yeah,
good to see. So please welcome Eric, and I'm going to be giving my microphone over to Scott. So please, come on.
All right, well, you can, thank you. This is going to be the Eric show, not the Scott and Eric show, so you can keep your mic.
Oh, that's dangerous. Very dangerous.
All right, but I am going to have to swap it. Make sure it's turned on. Yeah. Thank you.
All right. We probably need that. Leave it. Yeah. Oh, leave it plugged in. Okay. And I'll leave this.
All right, thank you. All right. Thank you. For a second, I've lost my mouse. Well, I don't know if you've all been at the usual trade show demo where things stop working and they all worked just a minute before. I lost my mouse.
You're also not sharing screen.
That is not under my control. There we go. Okay. The screen's not sharing. It did early this morning, so is there something I need to do? Close that, reopen it. It's showing somebody else's computer. See, that's bending it there, don't we? That's his cable. Oh, that's.
Tech guy in the room?
He's coming up. It's your.
This is what those magnets in this connect. Slide that one.
Let's start.
USB-C on this?
See, it worked this morning.
Yeah. Sometimes they just do not like the laptops themselves.
Oh, okay, no, that's mine, but it's not big. Yeah. Yeah.
Let's try this one.
How many engineers does it take to get a computer to work? Of course, I don't claim to be an engineer. I see. There's something with the percentages and signal stuff.
Oh, not extend duplicate.
Well, if it works that far.
Well, if it's duplicate, I won't be able to see my notes.
Yeah, that's why I'm just going to extend.
Yeah.
Another dongle.
There we go.
It was the duplicate.
Okay, there we go, perfect. Yeah. Okay. Whew, success. Well, so anyway, thank you all. We put on a little show there for you. Hopefully that was entertaining. As introduced, my name is Eric Reese. I'm a Senior Vice President with Kyokusha, but today I'm here as Chairman of the Software-Enabled Flash Project. And it's really exciting to be here, to be able to introduce Software-Enabled Flash to this crowd. Actually, some years ago, we made our inaugural presentation here to this group. And I really appreciate this group for the reason. One is you were the first to hear us, you were first to get excited about the concepts of software-enabled flash. And also I really like this more intimate setting of people who are developers who are focused on storage. And with that, I want to continue on a little bit with the presentation. But some years ago, we, roughly 5 or so years ago, we had been doing a lot of research with hyperscalers, with other people about where does storage need to go? Particularly focused on the data center, where does it need to go? There had been lots of things going on in the market about standard drives working in the hyperscale environment. Why are hyperscalers building their own drives? And we'll just get used to the flicker here. You can think this is like the 1980s or something like that. Your old TV, you can bang it a little bit and make it go. But I introduced the concepts behind where we can go, and we got a lot of interaction. So if time allows, I'd like to repeat that and leave a little bit of time for some Q&A. But we'll see how that goes. Well, we'll just hope that you can read really quick. Pardon me?
Can I run off the version on the other laptop?
I made some changes to that other version, so no. So we'll need to see what we can do. Oh, there we go. If you're wondering, that's a place called Waterton Park, Canada. That's a beautiful place.
You think it's the cable?
Skip.
Okay, I'll try to keep my thumb on as much as possible.
You'll get your number.
All right, well, I'll just keep going and we'll swap the cable when we get there. Okay, so much ado about nothing. Today I want to do a couple things, talk about the Software-Enabled Flash project, the evolving landscape behind storage and why something like Software-Enabled Flash is necessary, how SEF changes the way things are used, who should be looking at it, why you should be looking at it, and you know, what you can do to be involved since we're an open source project. Let's see if we can get it to. That's a little better, isn't it? Okay. So software-enabled flash represents an evolution in software-defined storage and storage itself. And the reason why is because we're trying to bring the media, the software, the solid-state media to you, the developers. And therefore make what was something as a predefined function element into something that's software definable. And with being software definable, we bring different elements of control to you, the developer. That would include placement, latency, isolation, to be able to prioritize your workloads, different software-defined protocols, and what's really important is actually a faster ability to migrate from one flash node to another. Okay. Yeah. I do. Okay. All right. Yeah. I guess the problem with the BYOD, right? Okay. So a little bit about the project. Software-enabled flash project is hosted and managed under the Linux Foundation. We're all familiar with the Linux Foundation, one of the gold standards out there in the marketplace. We're open source, and most importantly, I think in this particular effort, is we're vendor neutral. So even though I work at Kioxia, the project itself is vendor neutral and is open to all of you. And we'll talk a little bit about the end of the slide and how you can get more involved. Because it's open, we have a governance, I forgot I have a clicker here. We have governance processes and development process in place so that what is released is predictable. What is released has gone through a process so you can trust it. And we think that's very important. We oftentimes get asked about standards organizations. This, we believe, is one of the fastest ways to bring things to market. It's a predictable way, and by no means are we dissing or saying that standards organizations are not ideal. In fact, there's a history of projects moving into standards in the future, and that's something that we would definitely not oppose if that was the right thing to do. Of course, those who are members of the project would have to help decide that. Software-enabled flash is built for multiple implementations, meaning that it's not tied to a particular flash vendor, it's not tied to a particular controller manufacturer, it's open. I'm sorry. Finally, on the bottom left here, software development kits will be released as examples of how to do things. Command specs will be released. API is already out there on a GitHub. These things are, again, they're open. They're under, the source is going to be under BSD3 clause license, which is one of the most flexible licenses out there. If you go to the project site, you'll be able to link to the GitHub, and you'll find the API there and many other things coming quite soon. Just as a statement, I want to repeat time and again, we're vendor neutral. We follow all the antitrust laws. This is something your lawyers should have no problem with. Let me talk a little bit about the history of the project. So over the last 3 years, we've been releasing things on a nice and steady basis from year to year. But the history goes back before that. As I was saying in the introduction, we spent a good amount of time, the core members of the project, going and doing the market research with the future users, what we'd hope to be the future users of this technology. We spent a lot of time talking to the biggest names in hyperscale, presenting our ideas, getting feedback, and we had a nice feedback loop on that. And particularly the question is on your data centers, you're building drives. Why are you building drives? What is it you're trying to solve? Where do you see things needing to be in 5 years? Well, we're roughly at that 5-year period now. We've continued to bounce this information with those potential users, and we get a double thumbs up in terms of the directionality of this technology. It is what is needed. In 2020, I'm sorry, got some orange juice in my throat here. In 2020, we released the first concept on it as an FPGA to show what the API could do, what the technology platform could do. In 21, we released the first API as a reference, and that was a great reference tool. We got good feedback. Last year, we formally launched under the Linux Foundation as a project. And this year is going to be a great one because we've got hardware that demonstrates the API and all the concepts that we're doing. We'll have a reference SDK so you can get that thing up and going in your lab as easy as possible to be able to prove out the concepts of this and also to be able to get to further tune it to the needs of the market. So software-enabled flash is a union between hardware and software. We're not calling it software-defined flash because there's some things about flash that may not be necessarily definable, but we are enabling flash for control, particularly for behavioral control by the host. The hardware itself is purpose-built for this particular function. The software stack will give you the you developers control over placement, prioritization, over protocol use. These two are developed together to work seamlessly together from the ground up. So this was something where from the beginning we wanted to have the hardware and the software to be able to be unified. And therefore we have attained that. And if you'll download and look at the API and then the command spec in the future, you'll see how that works, how the two work together. In a beautiful heart of love. So I'd like to talk a little bit about the history, why this approach is necessary. Then we'll get into a little bit at a high level what it is. I'll make a pitch now, and I'll make a pitch later on in the slide. Scott Stetzer, who was introduced a little earlier, he'll be doing a technical track that'll go into a lot more about how this is done. I'm going to try to focus on the what it is and why it is. So. The historical background to this is, as I mentioned, there were self-builds going on. Why was that? Well, at the core of that really is that flash and SSDs had to work in an environment where they had to behave as hard drives. And in doing that, there was a tremendous amount of benefit that was seen, obviously. And SSDs took off, and we see them as they are today. But to be able to continue to play in that field of the hard drive, I would say, is paradigm, there are certain tricks that had to be, thank you. Certain tricks we've had to play with the flash to be able to make that work. And over time in its scale, that's led to some issues now that you need to see managed at the data center. And amongst those are latency, workload isolation, write amplification. Would have been nice if you'd opened it for me. All right, that's helped the dry throat there, thank you. And I'd say primarily amongst those is actually to be able to keep flash in totality and the TCO factor competitive with hard drives, we need to be able to make it cheaper and cheaper, which means you have to pack in more density into that. And so transition from TLC to QLC from one version to the other has always been a real headache for you developers. So these are some of the things in the background of why we wanted to take an approach like software-enabled flash. Because of those issues that I've talked about now, there have been efforts within the industry over the past 5 or more years to address those. And from the perspective of the project, these have been focused on more proximal issues such as wide amplification and isolation. And I think the biggest reason for that is because those are economic factors in the data center. But as I mentioned, from our perspective, these are somewhat proximal rather than dealing with the core of the issue. With ZNS and FDP out there having probably the greatest level of attention right now, we see those as subsets of what SCF can offer. SCF is not trying to replace these at all. What we are trying to offer is a technological platform where you can build from these and then build up and have much more headroom. So with ZNS, you have one form of controlling isolation, gives you access to the internals of the flash. FDP is really focusing on right amplification with placement control. And as I said, these are elements that within the software-enabled flash technology, we give you control over these and more is more of a superset. So as I was hinting, the approach of SCF is different. You know, how do we treat those other things that we've just talked about, such as ENS and FTP as a superset approach? When we were studying what the ultimate storage device in the hyperscale environment needs to be, we realized that a lot of those issues that the hyperscalers are dealing with were in that list that I showed just a minute ago. They had to do with flash needing to work within a HDD paradigm. And so if we were able to change that paradigm, if we were able to look at the stack from the media up and take a media-focused approach, what is it about the media that you need to do to keep it healthy, to have it high-performing, to be able to last longer, and to be able to really excel and take advantage of the digital nature of the solid-state device itself? What needs to be done? And that's the approach that we take, and it's more holistic. It's looking up into the stack, into the pain points of the stack, and giving you ultimately choices through software enablement to be able to control the behavior of the device in the way that's going to work best within your environment. So let me talk about what some of those elements are that you can adjust and you can work with. First off, isolation. Isolation is really an important factor in all sorts of ways. It leads to right amplification factor, it leads to data security, it leads to all sorts of things. And so what we've wanted to do in software-enabled flash is to be able to give you that isolation, starting at a physical layer and then moving up into virtual layers. So within a SCF-compliant drive, you'll be able to take that storage and divide it up into what we call virtual devices. A virtual device is more or less an isolation domain. And the only real limit to how many virtual devices you can create within a single SSD unit is really limited by just the number of die that's there. You can have you can have the whole drive be one virtual device down to as many as you need to make. Now, in our continued talking with customers, one thing that comes up right now with the higher and higher densities of SSDs is, is granularity. You know, perhaps one die, as dense as they are, is too much granularity. If you make a virtual device of some tens of dies or whatever else, you know, can you get the granularity you need? Well, with software-enabled flash, we want to be able to give that to you. So you can break each of these virtual devices into something called a quality of service domain. So where you have your physical isolation with a virtual device, you can then virtually isolate that down into subunits, what we call QoS domains, or quality of service domains. So you can take that granularity and you can continue to dial it in as needed. So finally, isolation is something that's under your control, and you can dial it in as you need, and it's not predetermined by the drive manufacturer. Latency outcomes. Once SSDs began to be used at greater and greater scale, latency has become an issue. And oftentimes, there was a famous paper some years ago by Google called Latency at Scale, or something like that. It was a good paper anyway. But it was called The Tail at Scale, that's right. As we all know, SSDs have to do things to keep the flash healthy. And that, when you have large scales, can lead to unpredictability in your latency. And that obviously is something that's not desirable. Based on your workload, you may want to have a really low latency workload. You may have another one that doesn't really care. Obviously, the most important thing when you're at scale is predictability. So within software-enabled flash, we give you that ability to be able to have a predictable latency on a per I/O basis. Now, we give you different tools for being able to control that latency. Probably the best and most, I think, dynamic tool that we have that I'll talk about here, and Scott will talk about others in his technical thing, is what we call die time weighted fair queuing. So at die time weighted fair queuing, you can set your parameters for latency. And the best thing about the software-enabled approach is once you've done that to the API, your drives can then come in underneath that, whether it be a TLC drive, MLC, or QLC, and it'll still just work because the drives are now compliant with the API. So every time there's a new form of flash out there, you're not going to have to go out and rejigger your stack. Those generational changes are abstracted away. Now, we do offer other types of queuing in there, not just the die time weighted fair queuing. There's round robin, there's other ones. This on latency happens to be one of those that we think is the most exciting. Data placement control. This ties together also with isolation. I think many of you want to have like data kept together. You want to be able to write the like data together. There's also the I/O blender effect that you have on standard SSDs, where the data comes in, it gets mixed up, and then it gets written to whatever die or most available. With data placement control and SCF, you're able to isolate that, to break that down, to be able to place and write like data together in a way that is predictable and deterministic on your part. One thing that I'd like to add to this is data placement is also a big factor behind FTP. We have a virtualized FTP device on this, so if you have apps that are working with FTP, you don't need to necessarily modify an SCF drive to have that work. So we have some tools available to be able to have a compatibility factor for that. Again, I want to stress that we see this as a technology, SCF is a technology that is a platform, that is a superset that allow you to be able to take advantage of what's now and then have a future-proofing effect going forward. Data placement also is something that's really important in write amplification factor. And write amplification factor is something that I'm going to talk about now. If you are good about or careful about placing your data, you can reduce your write amplification factor as well as the amount of time that you need to garbage collect. There's a lot of attention right now on write amplification factor in the market or in the industry because of its effect on power consumption within the data center. The closer you can get your WAF to 1, the longer your drives last, the better the health of your flash. Also, the less power that you're consuming in the data center because you're not rewriting, you're not rewriting. Through the placement control that I've already talked about, the isolation control that I've talked about, an ability of you to be able to deterministically decide when your garbage collection is or isn't going to happen. These are all things that are in your control for you to be able to adjust, to be able to get the best write amplification you can get for your application. I would not say that there's a one size that fits all here. There's going to be different ways that you run your applications, that your companies are running their centers that would have maybe different parameters. And what we want to do is be able to give you those control over those parameters so you can dial that down as closely as possible to 1. And 1 is the loneliest number that you ever knew. Hey, I knew this was the crowd that would get that joke. What was that? I'm giving my own age away. Multi-protocol. Now, this is probably one of the ones that I think is one of the best shiny objects that we have within the SCF technology platform. Is that you have the ability to deploy different protocols. Now, Scott in his technical presentation is going to be showing a video of a demonstration that we have using, I didn't want to jiggle that cable, using this device. So these are the first hardware samples. We will be having others in the future as well in different form factors, but this is the first one that you'll be able to have access to. And using that, there's a demonstration that will really showcase this technology. Now, within that demonstration, you'll see that one drive is going to be running multiple protocols at the same time. It'll be running ZNS, it'll be running block, and each of those on its own virtual device, virtual domain that I talked about now, or even in some cases within a QoS domain, running a protocol independently. Now, I don't expect that any of you in your real deployments are going to have one drive doing multiple protocols at one time. But what we're trying to show is that the capability is there for you to be able to deploy a different protocol on a drive in the environment or pre-deployment according to your need via software. So servers oftentimes are expected to have a lifetime of up to 7 years. Your drives are not going to be performing the same as they do on day 1 to day, whatever 365 times 7 is. There's going to be degradation over time, and oftentimes because of that degradation, then the servers are future-proofed and overspec'd. This allows you, looking at the TCO advantage and other things, to be able to not have to so future-proof your servers with this SCF technology platform, because you can redeploy those drives under different protocols as needed. Do you need to have a read optimized or a write optimized or some other form of protocol that's going to fit the workload? Well, you can do that with SCF technology. You can change it. Now, in some ways, oftentimes with the firmware, if you have a drive that you're going to deploy in some form, and once you've deployed it in that particular protocol, it's set for life. Well, that's not the case. Well, you can make that not be the case with the SCF drives and the technology. It can be redeployed. And the great thing is the demo, we can see how you do that. So again, as your workloads change or as the flash degrades over time, you can redeploy that drive, you can use it. You can actually change the over provisioning as well on the fly to be able to best manage its lifetime. That also begs the question about what do we do about the housekeeping things that have to be done to be able to keep the flash as healthy as possible, your garbage collection, your wear leveling, things like that. These are all deterministically under your control. You can schedule these operations to meet the need of the workload that you have. Sometimes we're asked, well, what if I don't want to do it? What if I don't want to pause it for garbage collect? What if I don't want to do a wear leveling? Or if we don't do it, what if I don't know the right time and I get it wrong? What happens? We have in the firmware, within the API, the firmware of the drive will send out a signal to the host saying, you need to do some garbage collection soon. And you can set those timers a little bit. However, if you continue to abuse your drive, we won't let you drive it into the ground. Ultimately, it will override and do these functions, but you're going to have lots of warning ahead of time before it ever does that. So I don't expect that unless you are intentionally doing it, that you'll ever have that problem. Also, we do have advanced queuing protocols so that you can queue these housekeeping things up so that they can happen in a time where they don't interrupt the real-time protocols. Now, I want to talk a little bit about control for all you OCD types out there. I've talked about control a lot in here because that's the idea. Is we want to bring the flash to you, the developers. So we've gone through this concept of the SCF technology in as thoughtful and a way as possible. As I said, looking from the media up, what is it that what control is it that we need to give you, the developers, over the media to be able to get the best performance, to be able to extend the lifetime of the media, to be able to have you really harness the control of the flash itself, being as wonderful a medium as it is. And I don't say that sarcastically. With the API, with this SCF API, we're going to be abstracting away the vendor differences. We're going to be abstracting away the generational differences. And we're going to be also abstracting away the different technological difference, being the bit density of that drive. So that if the drive is compliant and you've programmed to the API, from then on the drives will just work. And that's really the objective here, is that they're just going to work, because ultimately you'll have the control you need. How am I doing on time? Okay, what was that? We got 10 more? Okay, good. I was worried I wasn't going to maybe have too much time, but our technical difficulties. So let me talk a little bit about the business side of things. We talked about the technological advantages. TCO is a big issue. Obviously, total cost of ownership is really where it's at. Particularly since I'm paid by a company that wants to sell media. We don't really want to be focusing on the price of the drive itself. I don't think that the other vendors are going to want to be focusing on that. We want to talk about what's the total value. So TCO is really the best, I think, way to look at this. When I talked about abstracting away the generational differences, I know that as I've talked with key people at hyperscalers, the number one competitive thing that they want to have is to be able to transition from one generation to the next as fast as possible. Obviously, the more bit density, the better it is for them. And so one issue that drive manufacturers have is when a new media comes out, you need to be able to do the testing and do all that stuff to be able to have that drive warrantable before it's deployed to a customer. There's not a whole lot that we as a project can do about that, but what we can do is make the transition as easy as possible for the developers, and also reduce the number of items that have to be tested ahead of time. And if the hyperscaler, if you are representing a data center and you've adopted this API, there's a lot of things that could be under your control that maybe you can be doing the testing on your side. As we've gone through this, we're very confident that software-enabled flash technology platform will not only ease on the development side the ability to go from one generation to the other, but I do expect to see some benefit on the qualification side as well. That saying, just want to make sure I hit everything here. From a usage point, from a TCO perspective, that ability to be able to abstract away these generational changes so you can just continue to deploy the newest technology as soon as possible really is, I think, the best TCO improvement that we as storage vendors can provide. A few slides back, I talked about the multi-protocol abilities of SCF, and this also has great TCO implications. One of the most proximal of that is the ability to buy an SCF compliant drive without a specific protocol to it, Once you brought that in, it reduces your SKUs. You can then, as the user of that, deploy it in whatever protocol is needed. So, no longer does in this future world, no longer would a purchasing agent have to be too concerned about over procuring one particular type of drive. They can procure this drive and then deploy it according to the needs that they have, and have an easier way to be able to move through that inventory. There's also great implications on TCO for the drives that you already have deployed. As we've talked about already, as the flash begins to age over time, you have the ability to adjust over provisioning as necessary. You can adjust the workload. If it's at a lifetime where a read optimized is the best for that drive, then you can begin to deploy that drive in that way. So to extending the lifetime, the health, we'd expect if you're following these good protocols that your drives will last longer than maybe a typical SSD would, and if not, you still have the ability to be able to eke the most out of that you can over its lifetime. Finally, on the virtual device side, within each of those virtual devices, I mentioned that you have QoS domains. The overhead provisioning that you can do, the over provisioning control that you have, that would again lead to these economic benefits, can be done not only on the drive level, but at the virtual device level and also at the quality of service domain level. So, open source. I opened talking a little bit about why we decided to come to market first as an open source project. This is also, I think, something that has a great economic effect. Open source is actually right now receiving a lot of attention. It's receiving a lot more acceptance, particularly in the hyperscale world. And it also provides us a faster way to come to market, a faster way to bring the ecosystem together. There's not quite so many restrictions that you have in a typical fashion. And so this is the way that we've chosen to come to market, to be able to do this as quickly as possible in as open and vendor neutral way as possible. So, the Linux Foundation really provides a fantastic framework for doing that. We can be timely, open, vendor neutral, and I think the most important thing is it provides a structure that's both predictable and disciplined. And I think this preconception, I think, is getting dispelled now, but I think for a long time people looked at open source as the wild, wild west. Particularly in the framework under the Linux Foundation, that is not the case. We do have articles in place, systems in place, so that the process is predictable and dependable. Now, a lot of that happens within the TSCs, or the technical steering committees. These are held on a regular basis. We try to hold them multiple times a year. These are open to everybody. You don't need to be a member to be able to join the technical steering committee. We have one coming this Friday. I would encourage you to go to the website, register your name, you'll get an invitation. If you don't want to do that, just talk to Earl over here, raise your hand, or Sean over here. They'll be at the table. They'll take your name, they'll make sure that you're invited. If this Friday doesn't work, again, register your name on the website and we'll be sure that you're invited in the future. Again, as I said, you don't have to be a member to join and to participate. Your voice can be heard in that. It's the best place to be able to see what's going on with the project, what's coming down the road. And the TSC will have more information about when you can actually get hardware samples, when you can download the command spec, and when the SDK will be released. However, another call out to you old folks out, membership has privileges. Do you remember that one? Which credit card was that? Amex, that's right. I'm still using it. So with membership does come privileges. That is what comes through in the technical steering committees, what's going to be adopted, what's not going to be adopted. Paying members have the ability to vote on that. And so I would encourage you, we're open to new memberships, vendors, controllers, anybody that is interested, flash vendors, controller vendors, please, and anybody else, consider joining, consider having a voice on what's going to be released. Again, we want to have these things be predictable. So let me wind this up. Thank you for being here. Thank you for listening to us continue to bring this new technology forward. We're at an exciting time where it's now with the ability of being in your hands to test and to try. We got more information coming in this conference. The Birds of a Feather, not only will we be having Birds of a Feather, but we'll be feeding anybody who comes. Tomorrow at 2:30, Scott will be doing the technical show and tell, and we'll get a little bit more into the how these things are done. If you want to get the code or read anything, please go to the website. You'll also find out about when the technical steering committees are going to be upcoming, and that's also where you'll find notices about when the SDK, the command spec, and other things will be available to you. How much time do we have left? Do you have any time at all? 3 minutes? Okay, so we got 3 minutes for Q&A. Anybody got a question? Yes?
What's the license on the open source code? I may have missed it.
It's a BDS3. Mm-hmm. Oh, Scott, you wanted to? Oh, sorry. BSD3, okay, sorry. No, okay, BDS is something else bad, yeah. It's not dressed in leather. Any other questions? Yes?
I think you kind of touched on it, but when you give up this much control of your SSD, obviously a user can blow it up pretty quick. You said just like your underlying code in your SSD is going to safeguard the SSD from wearing out particular dies faster than they're supposed to make sure that if you have to override, you will override from a warranty business perspective.
Yes. Yes, so compliant drives that come from any vendor will have to comply with the API. The API does require that the drive send you signals about, hey, you're beating me up, you need to do that. I've also got Kurt here, one of our engineers. Do you have anything you want to add to that in terms of making sure that somebody doesn't blow their drive up? No, really? Okay, I guess I got it.
So is it that you just send warnings, or do you send warnings and then actually?
Actually, the drive will override and save itself. The drive will override it and save itself ultimately, but we trust that you will not force it to do so, because that'll hurt your latency. Any other questions?
Are you going to ship some reference implementations? For example, here's a read optimized profile, here's a write optimized profile, so we can see to get back to what the drives look like now and how you would do that with your software?
So yes, the SDK will come with reference implementations. So yes, the idea of the SDK being released with the hardware is so that people, when you put it on your bench, you can just fire it up and use it as quickly as possible without having to do your own coding. But you do have that, under this free license, you do have the source code, so you can muck around with it as you see fit once it gets going.
Any thoughts to management at scale?
Pardon me?
Any thoughts to management at scale and how to manage larger groups of them? Tool or mechanisms, or any thought going into that?
Management at scale. Boy, we could go on for a long time on that. What was that? Birds of a feather. Okay, yeah. Bring that question to Birds of a feather. It looks like I'm out of time. But yes, there are lots of thoughts about that. And to not be cute, yes. There are ways, and we've talked with vendors on how this can be, I mean, not vendors, but with future adopters and how that can be done. And then to be serious, yes, do come to Birds of a Feather. We can give you more. With that, thank you very much. Appreciate your attention.
Snia.
Your ongoing mission to explore strange new worlds.
Seek out new life and new civilizations.
To boldly go where no one has gone before.
So yes, my name's Scott Shadley, and I'm your MC for the rest of the day. Sorry you're going to put up with one of these for every one of our keynotes because I got to wake you up. So as we welcome our next presenter on stage, thank you, Eric, for the great presentation. It's now my pleasure to introduce our next keynote, Storage in Space, Enabled and Accelerated Edge of the Edge Computing on International Space Station. This talk is being delivered by Dr. Mark Fernandez, the only doctor I know that managed to get professors from 3 different universities to travel to him to get him his degree. So that's very cool and exciting. I appreciate that. He's now the Chief Scientist of Space Technologies and Solutions at HPE, where he spent 20 years creating, configuring, assisting in multiple types of technical, scientific, and HPC solutions. And they have put products on the Spaceborne Computer 1, or SBC-1, because we love our acronyms, launched in 2017, and in 2021 launched SBC-2, which pushed even farther into the HPC space, delivering results, insights to researchers and scientists, enabling deeper exploration of the cosmos. This has certainly put a new spin on the storage at the edge, which is always something we like to talk about here. And so without further ado, I welcome Dr. Fernandez to the stage.
Thank you, Scott. Live long and prosper. So hello, I'm Mark Fernandez. Great introduction. I'm quite honored to be here. This is especially special for me to be here today. A while back, my wife said, you need to start having things around you about where you want to go and what you want to do. And that's what's shown here, is the moon. I want to take storage and compute to the moon. We actually have a signed contract to do that in 2026, which is right around the corner. But today, where am I? I have an out-of-the-world data center up there on the International Space Station, populated with Kioxia SSD storage. We'll get into the details in just a moment about that. Excuse me. I'm with Hewlett-Packard Enterprise, HPE. We have the world's fastest computer at Oak Ridge. I like to rib my cohorts that mine is faster. It's running at 17,500 miles an hour around the world. Okay. All right, so why would we do this? Why would we want to put storage and compute out onto the space station, onto the moon, and onto Mars? And when I talk to the public and grade schoolers and other schoolers, I generally relate to the more modern movie called The Martian. And you may have remembered in The Martian, he's trying to communicate back to the Earth, and it took about 24 minutes to get a message there. So I want to relate that back to Apollo Mission 13. Houston, we have a problem, is how it's in common. It actually is, Houston, we've had a problem. Okay? So you're stuck in the mountains with very terrible cell service. You're out camping with terrible cell service. You're Ben Affleck or his friend here, Matt Damon, on the moon or Mars, and you send out a message to Houston. In 24 minutes, they get the message, okay, Houston, we've had a problem. They respond immediately. Does anyone know what the response was who hasn't heard my presentation before? Okay. Would you try turning off and on again? Yeah, correct. That is one thing. The actual response at 48 minutes, you're having problems. 48 minutes later, you hear, this is Houston, say again, please. We chuckle here on Earth, right? But this could be a very terrible situation. So, of course, you repeat the message, and over an hour before they get the message. So that sort of defines why we want to do this. I'm going to skip the technical part and say, Spaceborne Computer 1, we did a whole bunch of work to get that computer up into space. I'll cover that in just a moment. And then we were invited to the launch. That is a picture of my wife wearing a dress that she made, and it's covered with planets and stars and asteroids. And here we are looking out over pad 39A, looking at this new company called SpaceX that was going to try to launch rockets and do something ridiculous like reuse them back in 2017. Well, my wife was the belle of the ball. There were lots of teams there with identical logoed shirts and hats, etc. And she was feeling pretty good until this gentleman took the stage. We were quite honored to have Buzz Aldrin talk to us before the launch. And I sometimes have to remind the grade schoolers that he's the second man to walk on the moon. And one of the most famous photographs is taken by Neil Armstrong of Buzz Aldrin in Apollo 11 with the reflection of Neil Armstrong in his visor. When I'm talking to grade schoolers, etc., I generally stop here and do not point out that he's wearing "Get Your Ass to Mars" t-shirt. All right. Okay, so we launched at 12:31. If you've never been to a rocket launch, I highly encourage you to do that. This year, SpaceX may launch 100 times, which is 2 a week, so it shouldn't be hard to find one. They are very exciting, very thrilling. But what is even more exciting is to see that first stage come back and land and be reused about 8 minutes later. You don't have to wait long for it. Pretty exciting. All right, so my company has put together and approved this one-pager that tells you everything about Spaceborne Computer 1. I'll briefly go through it. In the far left, you'll see SpaceX taking off. Mark, can you take a modern, right-off-the-shelf, high-performance computing module and get it onto a rocket? Will it survive the shake, rattle, and roll of launch? Yes, we did. Once it's arrived there, can these non-HPE certified technicians called astronauts install it into a rack? Okay. There you see Christina Cope from NC State. Anyone from NC State around here? Go Wolfpack! All right, there she is working it. We did not plan this, but she's, of course, wearing an HPE-colored polo shirt while she does that. So, and on the far right, you'll see that we returned to Earth. That's a splashdown in 2019. The mission was 100% successful, and I'll get into that in just a moment. Prior to us splashing down, NASA asked us to do it again with Spaceborne Computer 2. What you see in the middle there is called a locker, and inside that locker are computers and storage. Inside that locker were 20 solid-state disks. First thing I want to point out is this is 2014-ish when we had to make this decision. SSDs were kind of new, kind of expensive. However, when we looked at the requirements to survive the shake, rattle, and roll of launch and get on board a spacecraft, to use spinning disk, there were extensive tests, one of which frightened me to death, and that was to determine the angular momentum generated by that spinning rust, and would it be safe for our $100 billion spaceship. Okay, you had to confirm that you could not throw the spaceship off a track. So we went with these very expensive solid-state disks, 20 on board, 9 of them failed. That's a good data point if you're NASA, not so good if you're a computer scientist or into storage. But I'll cover that in just a moment. All right, so let's go on to Spaceborne Computer 2. We went up on Northrop Grumman. You will see 2 lockers. NASA asked us to provide twice the compute capability with twice the length of the mission. So I've got twice as much storage on board, twice the compute capability. There we are launching in the middle of winter in Northern Virginia. And there an astronaut is installing into the overhead Spaceborne Computer 2. Here it is fully installed, power cables, network cables, cooling cables, etc. And I want to emphasize again, it is in the ceiling, all right? It's 155 pounds, but it's weightless, okay? So I often say as soon as Jeff Bezos can figure out how to get a data center in space, he will have at least 50% increased landscape into which to put his computers because he can put them in the ceiling. But we couldn't get a good perspective of this to talk to the public and others about how important it is to be able to put things in the ceiling, and we just kind of gave up. And then later on, this picture showed up in social media. And it is an astronaut watering the plants that they're growing on the space station. We're going to have plants when we go to the moon and Mars. And mentally, you want the plants to grow up. They're going to grow in whatever direction the light is coming to you. So those vertical, sideways, if you would, space on the International Space Station is kind of reserved for growing plants. And you can see above her shoulder, we photobombed her. So we are definitely in the ceiling. Okay? All right, so what did I send up? I mentioned I have 2 lockers. Inside each locker, there are 2 computers. You see them highlighted here in red in the upper one, so we can describe it as a GPU-enabled computer with 4 240 gig drives on board from our friends at Kioxia. And in the bottom, we have 8 240 gig drives. Now, back up, you saw I returned to Earth in 2019. I'm already getting Spaceborne Computer 2 ready to rock and roll. COVID hits. When I had 9 out of 20 failed SSDs, I said, I've got to figure this out. I'm going to try different technologies, different sizes, talk to some people. And everyone I talked to said, it's not going to matter, Mark. With COVID, we can only get you the 240 gig drives. That's all that's available out there. Okay? All right, so being conservative, I have 2 of these, 2 of everything. I put half of them behind a hardware RAID and half of them behind a software RAID, okay? Just to see if there was an effect. The hardware RAID cost me more up mass at $10,000 a pound, but I figured I needed it. And it's going to cost me more electricity, but I figured I needed it. I can tell you, as of today, it hasn't mattered one way or the other. I've had no loss of any SSDs, okay? All right, so before we're on a mid-mission refresh. One of the 2 lockers has been brought back down to Earth, and our friends at Kioxia have populated the GPU-enabled one with 4, I call them 1 terabyte M.2s, and 8 of the 960 gig 2.5 drives. So we're testing both form factors in various sizes. Okay? All right, so what are we doing up there? Whenever we talked about Spaceborne Computer 1, the most commonly asked question I had was, Dr. Mark, could you just gzip my data? It is taking forever to get my data that I generate. And here's an example. A scientist said, I have about a 1.8 kilobyte file, 1.8 gigabyte file. It's taken me 12 hours to get it down to Earth. 12 hours. I said, yeah, it's a Linux machine. Of course I can gzip it. So I gzipped it and I gave him 10x, which is not uncommon with gzip, right? I've never seen somebody so excited. He's like, I used to do one thing a day, and now you're telling me I can do something about every hour or so. This is just incredible. This is awesome. He was so excited. I could tell that the light bulb had gone off at what he was doing. And I said, so when you get this gzip file back down to Earth, what are you going to do with it? And he snarkily said, well, first I'm going to unzip it. Okay. And then I'm going to run the internationally recognized so-and-so piece of code on it that analyzes it. And I said, would you like me to do that for you? And that's when his light bulb went off. So we took his code, validated it on Earth, put it on the International Space Station. It was in a Docker container. And with about 6 minutes of CPU, GPU processing, we got him a 92K output file. It's 20,000 times smaller than what he's been dealing with, and I can get it to him in 2 seconds. Okay? So one of the first light bulbs to go off. Another one has to do with DNA sequencing. DNA sequences are very large. Depending on who you ask, they're in megabytes, gigabytes, etc. A lot of it has to do with the way they generate ASCII characters, and they only generate 4 of them, and they save them all, etc. But they are taking about a month to get one genome sequence down to Earth. Think about that. You run it a month, okay? But you're only interested in the mutation, which is either very tiny or hopefully non-existent, okay? So we went from 1 month to minutes giving them the results. And we are changing the paradigm. The light bulbs are going off. This NASA scientist had a written project to do 1 astronaut a month, and he was very concerned he wasn't going to be able to do it every month because of various other reasons. Well, now he can rewrite his project, and he can do the entire crew of 6 every day. And in his proposal, he's going to say, I could detect whether the radiation in the space environment affects Asians before Europeans, males before females, older versus younger. Now, these are large, so we have to be able to store them. We have to get them off of the storage confidently. We have to process it, put the results back out, and get those results back down to Earth. So that's what's critically important about what we're doing. Another one is there is lots of what's generally called Earth observations. They're taking photographs of the Earth, and one of the things they look at are lightning strikes. And did a lightning strike start a forest fire? Okay. Have you ever gotten a message similar to this when you have a photo on your phone and you want to send it out to a friend? Do you want to reduce this image size? Okay. Well, I don't think the firefighters and first responders really want to see the picture of the fire. They want to know where to go. So you can imagine the size of a photo going down to a text that just contains a latitude and longitude. So we're running the same software on Earth, but in space, confidently with our rock-solid storage and our CPUs and GPUs. Okay? Now, you'd like to get this done before that lightning strike generates a massive wildfire. And of course, we can also begin to look for illegal shipping, drug interdiction, and other Earth observations such as the polar ice caps. Okay. All right, one of my most recent ones and one of my most exciting ones is helping out with the EVA glove evaluations. They take a Nikon D9, pairs of astronauts work together. After an EVA, one of them holds the gloves, and they take pictures from various angles with various lighting, and those have to be sent down to Earth to see if the gloves are worn out, if they're safe to use tomorrow, next week on an EVA. Okay? So, excuse me. They have the processes here on Earth, etc. We move those up to the space station. Here's another one that I want to point out, that in this particular photo, there are 2 hands holding 1 glove. So you've got the 1 astronaut working the camera. This is the results of the photos coming back down to Earth and being analyzed with their artificial intelligence, machine learning. It will put a circle around areas of concern and annotate it with how much wear and tear is there. Okay? So we conducted this. 299 Nikon D9 proprietary high-resolution photos are brought down to Earth. The gloves are analyzed, and they get an answer in 5 days of whether or not they can reuse those gloves. Okay? So we were able to perform that, and we were able to give it to them in less than 45 seconds. Okay? So not only do we take the proprietary Nikon D9 photographs and analyze them, and those pictures that you saw are JPEGs, a more commonly understood and interpreted photographic representation that can be shared around the world. So we won an award for that. It was interesting. We had a 2-hour window to get all this done. The software had been tested and tested. It was running as it was supposed to, and we were done in just a few minutes. And they said, okay, Mark, we'll get back to you and tell you whether the answers are right or not. Well, they had to wait for the data to go down, do the normal processing. So about a week later, they called me up and they said, everything that you sent us was bitwise compliant with what we did on Earth. So 299 photos, raw, turned into 9 annotated JPEGs. You can imagine the amount of storage that we had to have available, be able to confidently read and process and turn into 9 JPEGs. And so they were extremely pleased. And then they said, Mark, did you know that you were able to process more than 60 photographs a second? And I said, yeah, I've got a low power GPU. I know the gamers do hundreds of thousands of pictures of thing. And he said, well, Mark, no, wait, you don't understand. If you can do 60 photos a second, that is equivalent to 60 frames per second. Would you be willing to try to process video in near real time? And the light bulb went off for me. I'd had dozens of light bulbs that I'd set off for various researchers, and this one hit me. I said, duh, of course. And so, here you see the real video as the astronaut is working, and they are beginning to see how and when the gloves are worn out. Okay? So this is going to save time and money from crew efforts. It's going to have incredible turnaround time so they can get back to work. I jokingly say that with today, you can do one astronaut and one EVA, and then he gets a 5-day vacation before he has to go back to work. If you're on the moon and you're trying to build a habitat, you kind of want everyone to begin to work every day if they can. And so with Spaceborne and our onboard storage and processing capabilities, 45 seconds later, we can put the gloves and have them ready to rock and roll again, so you can get to a 5-day work week. Okay? So, this is a bit of an eye chart. Each row is an experiment that we've done. We kind of talked about most of them, but I want you to focus on the column there in red font to begin with and compare that to the adjacent column in green. Because we have this reliable storage on board, and because we have the processing capability, we can go from 18 hours to 2 seconds. Or we can go from days to weeks to 11 seconds. Okay? Adjacent to each of those columns is the raw data size that we have to store, read, process, and then restore the results. The results are shown in that adjacent column of the output of the InSight size. That last column, I started recording how much of improvement we were giving. You saw the 20,000x, and with each experiment, more demanding on Spaceborne Computer, the improvement size went up. When I got to 179,000x, I began to think nobody's going to believe me. So that's when I switched to percentage reduction. So far, we've had no less than a 95% reduction in the download size. Now think back 20 years ago when you waited for the weekend to open up your cell phone and make a phone call because you're paying for the time. Okay? Well, if I can reduce your bill for the download by 95%, that is part of a business case moving forward. Okay? All right, so Kioxia finished the failure analysis on our Spaceborne Computer 1 SSDs after I had flown. I had done all that I could to be as protective as I could with the hardware RAID, software RAID, etc. But I got the failure analysis back. But I grew up in the trust but verify era, so I sent them the failed SSDs and one that hadn't failed. I was very pleased. They questioned, why did we send you this? Why did you send us this one? There's nothing wrong with it. So that gave me confidence in the rest of the results. The rest of the results were all of the others failed with the identical mode, and that was a supercap failure. And I was so pleased to hear that supercaps are no longer using that technology, and certainly not in the technology that's sent on Spaceborne Computer 2. Okay? So they assisted us with laying those out, and they got us a new SSDs in Spaceborne Locker 1. So I want to return to this for just a moment and very briefly go over what I think some of you call 1, 2, 3. I have my original data. Let's talk about something running on the red server at the top. I have my identical data on the red server. I make a copy of that on the red server on different media. Okay. I also put a copy of that on the white server below it, on the white server below that in a different locker, and then a third copy on the blue server at the very bottom. These servers go round robin as to who's going to download data to Earth, and an additional copy is placed there so that the data is brought down to Earth. So I'm extremely conservative, as you can see. I've got lots of copies out there. Hence, we were able to claim no errors in the first Spaceborne 1. Well, our reflight of our refurbishment got delayed by 3 months, and our friends at Kioxia came to us and said, hey, let's pull 4 of those 960s out and replace them with 4 30 terabytes. This is super duper exciting. So I've been pondering how to share with the public how large is a 30 terabyte drive, and I've kind of settled on it's 30 million megabytes. So your phone takes a photo and it's about a megabyte. An HD photo is about a megabyte. So 30 million photos on one of those drives, and I've got 4 of them on board. I can't officially claim it, but I'm pretty sure we've got more storage on the space station than has ever been placed in space. All right, I'm going to end with something inspirational and give you guys a challenge. Okay, I can now talk about this. It was presented at the ISS R&D conference just a couple of months ago. And as usual, it's got a very technical name, nanopore sequencing in space, the advancement of in situ. In situ is biology speak for edge. So we're on the edge of the edge. Microbiome analysis on the International Space Station by a NASA employee. This is one of his slides talking about the analysis that we did. At the bottom left, you'll see what's called a space station computer. A space station computer is a very old laptop. So if you have an instrument on the International Space Station, you're collecting data and you need to get it back to Earth, you first need to get it to a space station computer. And then the space station computer will put it on something called the payload NAS, PL-NAS. And it has a approved spinning disk on it. It's owned and managed by NASA. And when they have good downlink, they will bring your data back down to Earth. We have connected spaceborne computer to the payload NAS. And so the standard approved operational path continues as it is, but we reach in and grab a copy. So we reached in and grabbed a copy of the genome. We reach in and grab 299 photos of EVA gloves. We don't affect the operational as we prove for this experiment that it'll work. You'll see spaceborne computer there is dead center of the processing. It used to be wait 30 days and then you get the pictures that you see on the right. Okay? Now we've done the first sample to answer microbial identification aboard the ISS ever, and the results went from months to 24 hours, okay, on board the space station. So, and this is not possible without storage capability that's reliable and compute capability. So here's the challenge. This is in the abstract and bio of Christian's paper. We have changed the paradigm for doing this type of analysis. And we have changed the paradigm for many of these things. Solid-state disk and high-performance computers and faster networking are not going to change paradigms. It's what we do with them and what we help people to do with them that will change these paradigms. Okay? And with that, I want to thank you for kind attention. I hope I haven't run out of time, and maybe there's time for some questions. All right. Thank you. All right. Question for the non-storage developer guy. Yes. Yes. Okay. Multiple questions in there. We make multiple copies. That we still have to get it back down to Earth was part of it. And how long does it take? The times that you saw, I didn't bring that slide with me, but I've got a slide that shows a gigabyte, a megabyte, a kilobyte, etc., how long those will take. But believe it or not, we've got a whopping 2 megabit per second connection. All right? I don't think you could get that poor reception at your house anywhere. It's in the gigabytes, okay? So I make multiple copies of the raw data. I make multiple copies of the results or the insight. And to be honest, if the insights are telling the scientists what they need to know, they don't care about the raw data anymore. Okay? So they can get it whenever. And the whenever is next time I have the time and bandwidth to get it back down to Earth, or when I return to Earth, I'll give you the solid state disk. We've done both of those, okay? Yes?
Are you constrained by heat dissipation and thermal balance on the space station?
Excellent question. I didn't think this audience would want to hear about that. But I don't know if you noticed it, but Spaceborne Computer is water-cooled. We've put on the rear of it a miniature water-cooled door, and we tap into what the space station calls the medium temperature loop. There's no air conditioning on the space station. So it takes advantage of the technology used in homes in the north where they have hot water with radiators all around. Well, that medium temperature loop is set at around 72 to 73 degrees Fahrenheit, and blowers blow over it in order to keep the astronauts at the proper temperature. So we were given permission to tap into that, and we raised that temperature approximately 1/4 of a degree with our 600 watts. We were strongly encouraged to do that rather than put 600 watts of hot air into the crew cabin, which then the inefficient air circulation and heat exchange would have to take to get it back out anyway. So we're running about 85% of the heat goes out the medium temperature loop, and it has had been zero problems. It works very efficiently. Another little tidbit about it is the space station orbits the Earth every 92 minutes, and they have just enough ammonia in the radiators outside that it will not boil before it gets to the dark side, and it will not freeze before it gets to the light side. So it's a very delicate balance that they keep there. Interesting question. Yes?
For the SSD, I assume for the reliability reasons, it could be SLC or MLC. That's my first question. Second is, for the storage system, which RAID mode do you use? And third question is, where can we follow your work instead of wait until next year?
Where does what?
Where we can follow your work instead of wait for the next summer.
Okay. Let's see. The first one is easy. The last one's easy. Let me jump ahead to here. You can email me, or there is info/spaceborne@hpe.com. Okay? All right, so I will defer to the Kioxia folks about the technology underneath those drives. All I'm authorized to do is give you the make and model number. And to be honest, I'm an applications guy. I don't really care about the technology underneath. I want it to be fast, reliable, etc. And I'm changing paradigms with what I've got today. I'm very interested in the previous conversation, and I might want to test some of that on Spaceborne Computer too. The software enabled flash. Yeah, that may be a good experiment for us to run. Any other questions? Yes, sir, up front.
Do you have to worry about shock and vibration of these certified?
Yes. Back to his question. He had one more, though. What's the RAID configuration? RAID 1 plus a spare. Okay? Very simple configuration. That was recommended by our sysadmins as, quote unquote, the most reliable. I asked for the most reliable, not the most efficient, right? Not the most conserving of capability. I needed it to be reliable because 9 out of 20 had failed, and that's horrible. Okay.
Yeah.
All right.
A small question on rad hardening. Okay.
Just a moment. Say again. You.
So what about shock and vibration?
Shock and vibration. So we had to survive the shake, rattle, and roll of launch. Our company has a shake table, and it's set up for transportation via trucks and aircraft. So when we ship computers and racks of computers, so we ran it through that. SpaceX provided us with the three-dimensional G-forces versus time plot, and we're able to program that, so we did it ourselves. You then must go to Huntsville Marshall Space Flight Center, and they run it through their version of the shake, rattle, and roll table. Once you get on board the space station, it's weightless, and they move it around so slow and put it up and bolt it down. There's no more vibrations. Okay, so it's mostly the launch. Yes, sir.
Sorry, just curious about rad hardening. So radiation hardening, was any radiation hardening required for for the storage?
Excellent question. The whole purpose of this mission was not to do any rad hardening. So the gold standard for space flight computers is called a RAD 750. It's $200,000 for a dual-core 300 megahertz processor built in 1997, in which you'll have a hard time finding any programmers to operate on it because it's just not quite capable. So no hardening whatsoever. Your follow-up question is going to be, well, did you see anything? Yes, we did. We saw many more correctable memory errors, correctable data bus errors. We saw no uncorrectables. We have the two lockers in space, and we have their twins on Earth, identical hardware, identical software, and they too run the exact same software that's running on space, and that was our comparison. The modern technology was able to correct that. There are still many naysayers that don't believe that this is going to function on the moon. So we are in the works of having a radiation evaluation done and possible physical testing at a radiation site to see how they affect it. Okay? Very good question. A lot of things I didn't bring up because I didn't know you would be of interest of that, but like water cooling and radiation, etc. Got another one over here?
Yeah. So with the data the applications are using, how much of that, or is there a footprint of that that would be considered persistent? And if it is persistent data as opposed to just getting, data in, process, send out, and then flush, if there is persistent data, how are you guys handling that in case something happens to the SBC?
I think I understand that question, and again, this is another light bulb I turned off with the genetics people, was able to turn off with the genetics people. So their de facto standard is the human genome. So anything you do will run against them, compare against the human genome. Well, if an astronaut comes up with a mutation, then you're probably going to want to monitor him more closely. And that takes 12 minutes, et cetera, and gets you a data file, which is very acceptable in most cases. But I said to the scientists, well, if astronaut X has a mutation and we've been comparing against the human genome, why don't tomorrow I compare against yesterday's genome? And then if you get nothing, that's good news, right? And so there are numerous data sets like that A, are going to be reprocessed again. Secondly, we're in a machine learning, artificial intelligence, distributed learning fashion. So many of those coefficients and other factors are being saved and run back into the machine learning. What I do is I run what NASA calls a enclave. I'll run the same code on 3, if not 4 of the machines and compare the results. I don't tell the scientists I do this. They just think their code's running on this machine. They're very excited about it. But I've got 3 other copies, and I compare my results to his results before I even let him know that, yes, I think I got some good results. Why don't you go check them? Okay. Does that help? Thank you. All right.
We have one last question.
So the question is about the bottlenecks. What were the bottlenecks? Why the communication from space to the Earth, the data transfers took so long? Was it because of the protocols that were used and they didn't handle the latencies well because they were not designed for that? Or was it because of some other reasons?
So is the question about the bandwidth and latency to and from space?
And basically, what were the bottlenecks?
What are the bottlenecks? Very easy. A government acronym, TDRS, TDRS. It is a series of satellites that have been used since the Apollo era to communicate between spacecraft and Earth, okay? And they are the primary communications mode. Most satellites are one way. They do Earth observations and send down, etc. TDRS is there for communications, and it is 20, 30, 40 years old. And the maximum bandwidth, I think, is 640 megabits a second, but it gets chopped up among all the government agencies and then further sliced and diced. So spaceborne computer ends up with 2 megabits per second. The latency is around 700 milliseconds, which is incredibly high by today's standards. If you think back, if you were watching the moon landing and the conversations, you could kind of tell that there was a little bit of latency, you know. It's about like that. That latency to the moon is around the same 700 milliseconds because of the way that the path has to get back over the same satellites that were used to get back to the moon. So I can't fix that. So I often say, you know, when you're going to do something, you can make it better, faster, cheaper. I can't make things better because I'm using your TDRS satellites and your software, Mr. NASA scientist, but I can make it quicker and cheaper because I've got storage on board, because I'm doing compute on board, and I'm reducing that downlink by 20x. So saving you time and money, making it cheaper and faster. Okay? It's been a wonderful morning. Thank you very much.
Was a man that was sleepy, so the man brewed himself a pot of coffee, but the coffee did not awaken him, so he drank more and more.
In case you're wondering, we're on break until 10:40. Come on back. to the NAND solutions integrated with the CXL interface, highlighting their inherent advantages. He will provide an in-depth discussion on practical use cases, technical challenges, and preliminary findings to enlighten the community about the immense potentials of this technology. So CXL and storage, here we go.
Good morning. So, good morning, everyone. Thank you for joining my keynote today. As I mentioned, this is actually the third time. I have a different topic every year. Probably I don't have any more next year, but let's see. So I'm Yang Seok-ki, I'm Vice President of Samsung Memory Solutions Lab at San Jose. I'm glad to be here and have opportunity to discuss about the new opportunities related to CXL-based SSD. So, what this figure is about. So many people think the judging between stupidity and brilliance is simple. Oops, what happened? So this side. Because they know what is good, what is bad. But let's see whether actually that's true or not. But such judgment can change over time. So for example, when these two-wheelers were first introduced, 1900, observers of this saw them as nothing more than passing crazy. But this is actually the starting of the bicycle, right? But at the time, people didn't think this is a good idea. Similarly, when the first movie with audio track, this is the one, the Zed Singer was played in 1927. Many people thought that synchronized audio was just gimmick that won't last. But now all movies is with audio, right? So today I'm going to talk about a controversial topic in memory and storage community, CXL, the SSD with CXL interface. In other words, what if a storage device has a memory interface? What do you think about it? Is it good idea or a stupid idea? So before passing judgment, let me first discuss the needs of modern system, particularly in the context of memory hierarchy. So as you already know, the basic idea of the memory hierarchy is to keep the frequently accessed data close to the CPU to reduce data access latency. Memory close to CPU, memory close to CPUs has a lower latency and capacity, but have higher bandwidth, and so as a result, it is more expensive. However, this existing architecture are not well suited for the handling modern workload like big data and machine learning models because the working set is simply too big to fit in the main memory. So it's not fit in the memory. So storage class memory, which sits between DRAM and the SSD, provides comparable performance to the main memory and the persistence of the storage. CPU and BIOS recognize such devices as a persistent memory. Storage class memory has been used to provide low latency operation for large data through byte granularity access and to guarantee the fast and the lightweight persistency. For instance, this is the simplified version of Oracle, the Exadata system. So the Oracle Exadata used the storage class memory since its M7 series to provide large buffer cache and fast read logging. On the other hand, when the storage class memory is used as a device, log device, a few instructions that flush CPU cache and the memory controller queue can replace the hundreds of instructions across multiple software stacks to flush buffers in the host side and the device side. And in different contexts here, Intel DAOs was designed for high-performance scalable storage with byte granular storage access. It's also heavily rely on the Optane. However, as you know, the Optane, the Intel announced continuation of Optane, and many technology in the storage class memory area actually deceded. And the second topic is about the secondary memory. Historically, general storage devices have served as secondary memory, effectively extending the physical memory capacity through software implementation, either at the OS level or the user level. This approach aims to enhance TCO considerations. In this scenario, the CPU and BIOS typically recognize this device as a storage, not memory. This type of secondary memory is application agnostic, creating the illusion for the application that system possesses significantly the more memory than its physical constraint would suggest. For instance, the VDI, the virtual desktop infrastructure, each virtual machine often require quite a lot of memory, several gigabyte memory, physical memory, to extend the capacity without incurring the cost of additional costly DRAM. The VDI infrastructure typically use the swap space. But this strategy become economically favorable, especially considering that not all users are active concurrently. In a different context here, the Redis, the enterprise introduced an auto-tiering feature at user level. Auto-tiering extends the database beyond the limitation imposed by the available DRAM by employing the SSD. So Redis enterprise actually use SSD as extended memory. Auto-tiering proved particularly advantageous when there is a need for high-speed data processing over a substantial data volume. However, it is important to note that the software-based swapping and or tiering come with inherent cost. Its throughput is notably lower than the native storage performance, and excessive swapping and tiering can lead to the phenomenon so-called thrashing, right? So severely degrading the overall system performance. And the third kind of needs is about the fast small I/O storage. So high performance small I/O can help process metadata or temporary file, or small files, or fine-grained file access. Especially, we actually noticed to the recent kind of trend in the machine learning. The fine-grained file access is common in the machine learning models, such as recommendation system and the large language model. Different from the secondary memory, which conduct the tiering between the primary memory and the secondary memory at either OS level or system software level, the application for fast small memory are typically aware of such device and optimize for high performance small I/O. For instance, this is the recommendation system actually Meta announced a few years back, and they are heavily using this model right now. The recommendation model, like DLRM, leverage embedding tables to reduce the computational complexity associated with sparse items, meaning that if you go to the Amazon, there are a lot of the product and the items. They actually have to represent each of them using some representation. So that is the sparse item, and they store that information in the embedding table. Typically, the entries within embedding tables are very small in size, ranging from tens to hundreds of bytes. So, which is quite different from the unit that usually we provide for storage. It's 4K, right? So then how we can actually improve the access to such small kind of data in the storage. You may argue that why you want to store that there. You need to use the DRAM. But as you can see, this embedding table size is growing very fast. And right now it's more than terabyte. And the 2 years back, this year going to 2 terabyte, next year going to be 4 terabyte. So it's keep increasing quite rapidly. So it's very challenging to store such big embedding table into DRAM. So there are several papers from Meta and NVIDIA whether they can use SSD to store such embedding tables. So it is important note that the most storage device conventionally employ 4K page size as a default unit of data transfer. But as I mentioned, this use case actually is different from the traditional one. So consequently, the majority of product available in the market do not deliver the higher the IOPS performance for small I/O. So if you measure the performance 4K I/O on the 1K I/O, 512 I/O, whether its performance getting better, mostly not. It's almost same or actually goes down. So then why do they want to do this? Because it's bandwidth limited, basically. If you can have more IOPS, you can do more processing. But if you do the 4K I/O, then what are you going to do if you need only 128 bytes out of it? Then majority of bandwidth basically wasted. How can solve this problem? One way is to provide more fine-grained kind of access to the device. Then you can save bandwidth and improve performance. That's the wish, but actual device does not provide better performance with small I/O and even worse. So we have sort of a dilemma right now. So the needs for the storage class memory, secondary memory, and fast small I/O are not something new I addressed in this talk. Everybody knows this for a long time. So then why I'm talking about here? So I argue that the hybrid of DRAM and NAND can form a family of product concept to address the needs in the industry in a consistent manner. I call the family of concept as CXL-based SSD, but I use CXL-based SSD as general concept, which encompasses a variety of use cases built on top of SSD technology. Please note that the CXL-based SSD is not a product name or a trademark from Samsung, because CXL, we have to use the term very carefully. So again, it has nothing to do with the Samsung directly, but I use the CXL to explain what kind of device concept I try to explain in this talk. So since I believe most of you already know CXL, so let me briefly touch base on the CXL to have a kind of context. According to CXL consortium, CXL is cache coherent interconnect for processor, memory expansion, and accelerator. The CXL consists of 3 protocols: CXL.mem, .io, and .cache. So first, the CXL.mem provides a host processor. This is a host processor with access to device attached memory using load store semantics. On the other hand, CXL cache allows peripheral device to coherently access the host memory with the low latency request and response kind of interface. CXL.io is functionally equivalent to CXL protocol with some enhancement and used for initialization, the link up, and device discovery kind of thing. So it's mostly for management. And the CXL consortium also kind of classify the CXL device into 3 types, 1, 2, 3. And even though there are some confusion about the device type, in essence, the device types are determined by the protocol the device actually support, not functions that device provide. So sometimes people say accelerators type 2, but it is not. It's based on what protocol the device support. Among the protocol, CXL.io is common for all types because the device management, as I mentioned, and configuration is done through the CXL.io protocol. But if you add CXL.cache to the device, then we call such device type 1 device. If we add .mem to the device, we call such device type 3 device. If you support both of them, meaning the .mem and .cache, then we call that such device type 2 device. So if there's no actually additional protocol except the CXL.io, such a device is a traditional PCI device. And in that case, we may want to use CXL.io as a data path as well, not just for the management. So CXL-based SSD consists of DRAM and SSD, but its functionality can be very diverse. So in this talk, I categorize the CXL-based SSD into 4 types based on various device features and characteristics. First, here. So a CXL-based SSD can be used as storage class memory, say the persistent memory, if DRAM space is advertised as a device memory space via CXL.mem, and the NAND is used as a backing store in case of system shutdown, reboot, or power failure. Second, CXL-based SSD can be used as secondary memory if the NAND space is advertised as the main device memory via CXL.mem, and the DRAM space is used as a cache for the NAND space. And third, CXL-based SSD can be used as a storage as it is if NAND space advertises device storage space via CXL.io, and the DRAM space is used as a cache for the page of storage. Last but least, CXL-based SSD can be used as a combo device of memory and storage. And if DRAM space is advertised memory space and NAND space is advertised as a storage space, meaning that it's just you combine memory and storage together into one device. Then why do you want to do that? You can actually manage the memory more efficiently for storage, and the data transfer between the memory and storage can be optimized. So all the CXL-based SSD except the storage use case are actually CXL type 3 device in the context of CXL type. So even though we say CXL type 3, there are many different type of devices. So it's very hard to differentiate between these. So because of that, I'll talk about the type, the CXL-based SSD type, even in the CXL type 3 device. And in addition, this device architecture may remind you the NVDIMM technology in mid-2010, right? So there are many different types of NVDIMM, NVDIMM-N, NVDIMM-F, NVDIMM-X, NVDIMM-P. So there are a lot of words related to the concept, and they are mingled together. So I'd like to clarify what I'm trying to say through the CXL-based SSD types. So let me talk about the CXL-based SSD as a persistent memory. I assume that you are familiar with NVDIMM technology. It's okay you don't know. I'm gonna rephrase what each device actually means in the NVDIMM technology. So you don't need to worry about that. But pretty much many people here already know what is NVDIMM technology. The standard body JEDEC defined. Right? According to the spec, both NVDIMM-N and NVDIMM-P combines the feature of DRAM and flash, and the computer have a direct access to the memory module, supporting both block addressing and the byte addressing. CXL-based SSD as a persistent memory similar to NVDIMM in the sense that the DRAM space is exposed. Here, what is exposed to the system is actually DRAM space, even though we have NAND, but NAND is used for backing store when the reboot or the power failure happens. However, the capacity, the latency, and durability requirements are close to actually those of NVDIMM-P. So at the first look, looks like NVDIMM-N, but the detailed requirement is not quite NVDIMM-N requirement, it's close to NVDIMM-P requirement, as you can see in the table. NVDIMM-N targets small capacity and low latency at the level of tens of nanoseconds. So 10, 20, that range of nanosecond, while NVDIMM-P target much larger capacity and the medium latency at the level of hundreds of nanoseconds. Then we have to know what is CXL latency, right? Typical CXL controllers show latency over 100 nanoseconds without actual media access. And the device can support tens or hundreds of gigabyte space, and it also support the GPF, Global Persistent Flush feature, to make sure that the persistency is guaranteed. So I already introduced several types and from NVDIMM perspective and the CXL perspective. It is mingled right now. So the device I'm talking about here, CXL-based SSD as a persistent memory, have different characteristics compared to existing technology. So this is the kind of the requirement or actually performance we actually see in the real product. So this is the simulation, the kind of animation, what happens. So when power failure happens, how device is going to respond. So in general, so in the normal situation, when you write data from host to the device, and that data is written to the DRAM and in the device. But usually we may have the battery to support power failure. You don't need to write back the data to the NAND in the normal situation. But if power failure happens, then the system may want to maintain the host level power using the backup battery or the backup power to maintain the PCI slot live. And the CPU will start to flush CPU cache and the memory controller buffer to make sure that all the data in the cache and the memory controller is written to the device. And at that point, the device use its own battery and make sure that all the entire content in the DRAM cache is written back to the NAND backend store. And when power comes back and the device load data from NAND into the DRAM and provide data from the DRAM to the system. That is the kind of the typical scenario with NVDIMM-N, NVDIMM-P, and CXL with the CXL 2.0 GPF functionality. And we have, as a prototype, Samsung has a kind of prototype to implement this functionality and compare the performance to the existing solution. This slide shows that the persistent memory performance bearing the read-write ratio. The CXL-based SSD shows consistent performance for read and write. You may be wondering why. Because it is mostly limited by the CXL bandwidth. So usually the internal bandwidth in the device is much higher than the external bandwidth, but from host perspective, it is not observable, right? So it's primarily limited by the CXL interface. And as you see, the read percentage increase, CXL device performance get closer to the DDR5. And it also showed that CXL SS showed a much better performance than the leading the personal memory technology, especially when the concurrence is very high. So, so this is the video clip. Oops. Oops. How can I click this? Okay, so let me skip this. I don't know how to play the video here. So basically, we actually developed the system, and this video is basically capture how the system can shut down and reboot. So the prototype we developed is working well in this kind of scenario. So in this demo, we use memcached and with the CXL-based SSD and populate 1 million items, and the system is rebooted. And whether the memcached is restored at the state it actually shut down. Okay, so the second device type that I talk about is secondary memory, right? This device provides secondary memory different from the traditional ones. The traditional secondary memories rely on the host software to give an illusion to the application as if they have more physical memory. That is, the device for secondary memory itself is not a memory device. Actually, it is a storage device from the CPU perspective. In contrast, CPU recognizes the CXL-based SSD as a memory device. The NAND space is exposed as a memory capacity to the host, like NVDIMM F or NVDIMM X, or even NVDIMM P devices. This CXL device type supports both block addressing and byte addressing, similar to NVDIMM P. But NVDIMM X targets the medium latency at the level of tens of microseconds, while the NVDIMM F targets medium capacity at the level of sub-terabyte. So it is not exactly one type from the existing NVDIMM technology perspective. So CXL-based SS consists of DRAM and NAND, depending on the how DRAM and NAND is used. The three options is possible. Simply put, you can expose in the NAND space as main memory, and then you use host DRAM and the device DRAM as a cache, different level of cache. Or you can use host memory and the device as a memory extension. So the cache DRAM in the device is not visible to the system, it's at play as a cache. And the last option is you can expose all of them to the host and let host manage based on their needs. So host DRAM, device DRAM, and NAND space as mapped to the HDM, the host, manage the host manage the device memory, and the host software manage all the memory region exposed to them. So even single device, there are many options to manage the devices. So it's hard to see here. So depending on the option, you may have different choices, but this one is option 2. Basically, you use a device as a kind of extended the memory and measure the performance, what is the kind of performance implication. But this graph basically said if you have a good cache kind of hit ratio, device performance is close to the interface bandwidth. But you can see that is very critical how to manage cache efficiently, because here is 90%, this is the 100%. If you cannot keep the cache hit ratio very high, the overall performance is not going to be good. So how to manage cache efficiently is going to be very important. So and the last one is CXL-based SSD as a fast small I/O. And again, this one is not correspond to specific the NVDIMM type. It is a mixture of them. And the basic idea is that, as I mentioned in the previous slide about the DRRM example, we want to access small data, smaller data than the 4K. And how to implement it architecture-wise is going to be similar. So you read the data from the NAND and into the cache in the device, and you provide finer grain kind of data to the system. By doing that, you can actually reduce the amount of data which is wasted in terms of bandwidth. So then from a host perspective, how you can handle this. So it is a combination of the CXL.mem and CXL.io. So from host perspective and the user's perspective, it can think is a kind of hardware-based mmap. So you have storage device and you have LBA. That LBA is exposed to the host, but you have a way to access the LBA space using memory protocol as well. So from the host perspective, there are two options. You can have a 4K I/O or small I/O until system support, meaning that up to 512, you can actually do the block I/O, and this device is gonna cache page into the DRAM and serve to the device. But if you want to go further and smaller than the 512, then you can actually use that MEM protocol to access fine-grained data like a 64 byte. So conceptually, as I mentioned, it's mmap. So you have LBA, and you expose that LBA space through the memory space from 0 to a certain capacity, and that memory space mapped to the physical memory through the HDM, and the application actually map that the physical address to its virtual address. This kind of mapping gonna happen in the system, but the difference compared to existing mmap, it bypassed page cache. And the performance when you use this device for the meta DRRM case, as you can see, this is actually example. You can use NVMe device and do all the operation, store the embedding table in the NVMe device and do the operation using I/O stack. Or you can use host memory as a cache and do the I/O using NVMe device. Or you can use CXL device, the CXL-based SSD, as a kind of high-performance small I/O device and measure the performance. The basic idea here is that even though you can do the host-based cache, by reducing the amount of the data transfer device, you can actually improve performance. So let me skip this one. So I talk about several kind of the use cases, how CXL-based SSD can be used. But the thing is, as I mentioned, this is different from CXL types 1, 2, 3. It's different from the NVDIMM protocol. So we may need a kind of standard and the ecosystem to drive these technologies. And another concern is that the latency tolerance. So this graph is another kind of representation of the memory hierarchy. And the device that I mentioned here actually correspond to 1, 2, 3 there. And the question actually, if we have this kind of device, can CPU support this? And the CPU typically can handle only hundreds of microseconds, several hundred nanosecond latency. And if you take longer than that, they have an implication because CPU need to do the kind of out-of execution using the real buffer. But the most of CPU right now cannot handle this properly. But it is not just the CXL-based SSD issue. If you're using the CXL 2.0, 3.0, you have switch, and the switch have multiple hops, which add around 100 one way. So you just go to the around 500 nanosecond latency. So how we can handle this one? I expect the CPU vendor are going to address this problem properly and handle the issue because it is not just CXL-based SSD issue. It is fabric issue as well. And the cache management performance is very critical because the device, how you kind of configure device is up to the vendor, but the managing the DRAM inside device is very critical for overall performance and functionality. So I'm a little bit rushed, but let me wrap it up. So CXL, SSD with CXL interface can have various use cases. And I talk about persistent memory and secondary memory and high performance small I/O, and also can be a near data processing platform. But the issue is that actually there is no clear definition about what it is and how we're gonna handle this and what is the benefit to the system. So Samsung actually the driving this effort and wanna work with the community to build a standard and ecosystem together. And also the CPU vendor need to actually address the CXL technology properly from the latency tolerance perspective. GPU case may be okay because they have many cores, so you can hide the kind of latency issue properly, but CPU side, we need to dig deeper how it can be handled properly. Okay? Thank you for listening, and since it's almost time's up, so if you have any questions, you can do a few, or I can do later. Okay, thank you.
All right, thank you very much. Our next presentation.
Pencil sharpening. Everyone knows what it is and almost anyone can do it. But can anyone claim they're actually good at pencil sharpening?
All right, our final keynote addresses the topic of sustainability. We're here to listen to Dr. Eric Reidel, the coolest CEO because he's the Chief Engineering Officer of Flax Computing, to share his paper on sharpening our pencil on carbon measurement and reduction. He's a former Snia Technical Council member and has worked on organizing the Object Storage OSD and Green Technical Storage work groups, and a longtime participant in the open source Linux efforts in storage and scalability systems. Today he's going to show us how to use carbon footprints as a common metric to assess a set of computing equipment that allows straightforward comparison of technologies and designs on a performance per carbon basis. And since he's ready to go, I'll stop reading and let him have the floor.
Thank you, Scott. Beautiful, yeah. So we're gonna talk about pencils and we're gonna talk about carbon. So hopefully I'm gonna motivate why kind of using carbon as a common way to think about your data center is gonna make your data center more happy and save the world. So here's my pencils. So what I'm going to propose, or what I'm going to try to motivate here, kind of the last few years of my experience in kind of sustainability, but really my 20 plus years of engineering experience. And so there's a lot of different colors here, a lot of different ways that things can be measured in your data center, a lot of things that matter. But I'm going to try to motivate that if we can reduce them down to kind of carbon footprint, then that'll be a great way to optimize your data center kind of in two ways. And so I was told many years ago to put your your conclusion up front and don't make people wait. So this is my conclusion. So my conclusion or proposal is that if you look at the carbon footprint of what you're doing in the data center, so the energy consumed in the data center as well as the energy that was used for the inputs in the data center, and I'll talk about that at some length, kind of scope 3. But if you use what is the current carbon footprint of your data center, and you look at how can I reduce the carbon footprint, then there will be a lot of ways to reduce the carbon footprint, most likely. And the good news is this is not like solar power or electric cars where you have to invest more or spend more and then you get this benefit down the road. This benefit is immediately obvious, and if you reduce the carbon footprint, you're going to reduce your cost. So that means from the point of view of a data center operator or someone paying for all the various pieces of the data center, you're going to reduce the carbon footprint, which is good for the planet, but you're also going to reduce the cost footprint, which is good for your bottom line, right? So this is not kind of a trade-off. This is all in better, and that's what I hope to motivate. SW kind of recruited me or dragooned me onto the stage here after I gave a talk at the Mass Storage Technology conference a few months ago over in Santa Clara. There's a longer intro in that talk if you want to look at these slides, so you can click through, but I'm not going to give kind of longer intro of long-winded ways of my pathway through storage and all the things I've seen, but I've seen some stuff, right? But I want to give just one example of when I joined EMC in 2008, the problem I was given to kind of optimize the hardware team was this system. So what we were building was an object storage system that was going to be sold or was being sold on dollars per terabyte, right? And dollars per terabyte was a great metric for us because we could optimize this from an engineering perspective. And so that meant I had a rack. I had to put disk drives in this rack. I had to connect all these disk drives together and eventually hook them up to an Ethernet interface so that someone could send a REST API. But the optimization factor for us was this entire rack. So we got well-formed REST API requests in the top of this rack as Ethernet packets, and whatever we did inside the rack was completely up to us. So that means that from an engineering perspective, we could do not only hardware co-design with all the components that are in here, but also hardware software co-design with. We determined the file systems that we put on these drives. We determined the protocols that were used between the servers. So this gave us an incredible amount of freedom of action to optimize this metric, right? And so dollars per terabyte was our headline metric. But remember I said this was 2008. So 2008 was the early days of cloud, right? So I remember sitting in a boardroom meeting with Joe Tucci, and he's like, "You mean that like the Amazon, like the book guy, like we're going to compete with the book? What's going on?" So this was the early days of cloud, right? But we were already starting to talk about, and this is what the cloud gave us, right? Dollars per terabyte per month. So not just the upfront cost of how much was I going to pay for the storage system when I bought it, but what was the all-in ongoing cost. And I'm going to propose that this has proven true over the last 15 years, basically, certainly 10 plus years, that if you look at the all-in costs of what you're doing, you can get a much better end result than if you just look at the purchase cost ongoing, right? So what was our optimization model here? We had to put, so dollars per terabyte, right? So that means that the more terabytes I could put on each drive and the more drives I could put in the rack, the higher my terabytes, right? And the less overhead I had, the less of these pesky servers and then all these cables and backplanes and chassis and pieces of sheet metal and so on, the better off I was going to be, because all those other things just add to the dollars and they did nothing for the terabyte, right? So every piece of overhead I added was going to increase the dollars, but not do anything for the terabyte. So what did we do? We looked around, different enclosures. This is what was going on at the time, right? Backblaze was here yesterday, I think, giving a talk, right? Maybe folks know they're very bare sheet metal, red enclosure, but there's lots of different systems, the ubiquitous kind of 2U12, Super Micro had a SNEA system for a while where you had the disk drives in the front and in the back, so you had to walk to the hot side to get the disk drives. SGI introduced this idea of trays. Those trays are going to come up again where you mounted the drives, and we had this back-to-back, right? And so what we did is we looked at how else can we rearrange the physicality of this, right? And worked with some of the enclosure suppliers and ended up with this configuration that's now basically ubiquitous in high density storage, right? Disk drives in what we unfortunately call the tombstone configuration, right? So the drive is put into the enclosure, the weight of the drive pushes it down onto the connector, so you don't need fancy brackets, braces, and so on. You have minimal sheet metal protecting the drives, and you're still meeting all of the engineering CTQs of those drives, right? That brought us up to, sorry, I didn't mention the metric. So the metric where we started was 8.5 drives per U. This system brought us to 14. We eventually had another enclosure that HCST helped us kind of innovate with that was 22 drives per U, right? So in that system, we put 800 drives into a rack. We used, in our densest configuration, just 4 servers to get enough redundancy. We were doing redundancy in software, right? So compared to my other architect friends at EMC, they were like, gold plating, platinum plating things. No, we couldn't afford any of that, right? This was silver plated at best, right? We didn't do dual pathing. We didn't do various things. We used software erasure coding across the Ethernet, SATA drives, high density. We experimented some of these systems, at least at the experimental level. We even did zones before zones were cool, right? So 800 drives, 4 servers, 2 switches, 18 cables. So each of the servers had 2 cables to the 2 switches and 1 cable to the JBOD, right? So minimal in the design, right? And one of the big reasons we could do this is because we were end-to-end optimizing, right? We didn't need to interoperate with hundreds of different ways to do it, all different kinds of arrays and servers and HBAs and multipath and all this stuff that my other architect friends at EMC, they're like, oh, Eric's life is so much easier because all he has to do is put some drives, right? This allowed us to be, at least at EMC, we were the first group to use 8 terabyte drives. Use helium drives, right? Everyone's like, oh my God, Eric's gonna use those helium drives. What's gonna go crazy? Like, they were twice as much capacity as the drives we were using. Of course we were gonna use them, right? So we used tens of thousands, hundreds of thousands of those, right? So we built several exabytes of this in 2 generations of products. We then iterated again. We ultimately did, 7 generations of hardware between these 2 platforms, put a bunch of exabytes out, right? By being able to do this end-to-end optimization, reduce, because we had our dollars per terabyte per month. And a couple of exabytes that we put out into the world kind of were child's play compared to what was done in the cloud space, right? GFS was built on these same principles. The original kind of big shift from the GFS paper when it was presented in the research community was they were going to break the API that was given to applications, right? So we weren't going to be backwards compatible with what a file system expected because they wanted this efficiency in all the layers. And that folds down into all the layers. Colossus still built like that, okay? So now, hopefully, I've motivated kind of end-to-end motivation, do more with less, because you have a metric to optimize, right? But I said I was going to talk about carbon, so let me talk about carbon, all right? It's my pencils. It turns out I was actually exposed to environmental thinking or carbon thinking actually very early in my career. So my first job in grad school was actually with the Electric Power Research Institute here in California. I put this map up because I eventually recognized this building when I kept visiting VMware. We were helping them with their cloud service. And then at some point I'm like, wait, this looks familiar. And it turned out, I just turned left instead of turned right on this road. And there was this place where I did my first consulting gig kind of 30 years ago, right? And similarly in Snia, so here's a slide from SDC in 2009. where SW, myself, a small group, Leah, who's here, small group, half a dozen folks, maybe ultimately grow to 24, created the Green Initiative within SNIA. It's still running today, right? And we were looking at the power efficiency of storage systems, right? The guy that we talked to from Energy Star, he was so excited. There's a guy named Andrew Fanara, was so excited to deal with us. He had just finished optimizing Energy Star for refrigerators, the coolers where you get water cooler, so on. And he's like, oh my God, it was so terrible. We just said, like, what are you talking about? There's a hot pipe and a cold pipe and like a little bit of insulation. What? And so he's like, and then when we started explaining to him about how storage worked, he's like, oh my gosh, there's so many different avenues. You guys can do so much, right? And that's what we've been doing, right? There's so many ways to optimize the energy consumption of your storage system that this has been 15 years worth of work, right? But it's not just energy, right? There's a lot of resources that go into our computing, right? A lot of kind of fancy metals, things that have to be brought out of the ground, right? I was at Seagate during the great ruthenium shortage, right? How many people knew there was a great ruthenium shortage? Yeah, there was, right? It has to be brought deep out of the ground. There's a lot of metals that have to be brought deep out of the ground, right? So there's a lot of underlying resources. And I'm taking a small shortcut in that it isn't all carbon, right? Some of it is ruthenium and copper and tin and so on. But you can normalize a lot of that to carbon, right? How much carbon does it take to extract the ruthenium from the ground? And you can still get pretty close. So kind of carbon equivalence is really what I'm saying, but hopefully you'll pardon me the rounding, right? And so the important thing, and the thing that I was introduced to about 5 years ago when I was dragged into, when I joined IT Renew, is you want to look at this number. So this is my second slide of bringing the conclusion up front, right? And so in a typical server scenario, more than 75% of the lifetime carbon of a piece of computing equipment has been expended before you plug it into the wall for the first time, right? And then we have, in this example here, 22% is all the energy consumption while it's running in your data center, right? And then there's a couple percent that's spent kind of after it leaves the data center, when minimal, right, as you deal with that, right? But 76% in the upfront case, right? But if you think about this for just a few minutes, right? This is highly sensitive to what you're actually going to do with the server. So this is if you run the server for 3 years. If you run the server for 6 years or 9 years, then that operational phase becomes much higher, and it pushes out, amortizes that pre-use phase, right? And so that's what we're going to motivate in the next couple slides. So what we did at IT Renew, when I joined IT Renew, we folded into something that's in the general world is called the circular economy, which is basically extending the supply chain, extending the lifetime of systems, right? And so this is Ali Fenn, my former boss at IT Renew. She kind of motivated this. She was also involved in object storage, so we had kind of a bit of a history through Snia and so on. She ran the Kinetic program at Seagate, if people remember that. But the important motivation was that so much energy, no pun intended, had been spent optimizing that operational phase, right? Reduce the energy consumption, but very little attention had been paid to the upfront cost. And the numbers here are huge. So this is from a presentation at OCP in 2019, and it was motivating in the next 4 years, so 2019 through the previous 4 years now, right? So there were 65 million servers in data centers, and there were going to be 14 million additional servers deployed over the following 4 years. So the logical thing is, okay, that right now there should be 120 million servers in data centers. But it turns out that's not the case. It's a little bit lucky because it would use even more energy footprint. But so it turned out the number, an expected number, was more like 75, which meant that almost 50 million servers would be brought off the data center floor and create basically e-waste, right, in that same time period, right? And this is what that looks like. So this is the IT Renew processing facility in Kansas. This is about 600 racks, each with 30 or 40 servers in it. So this is 15,000 servers that are on their way to the e-waste pile, right? When in the time that I was with IT Renew processed between 25,000 and 125,000 servers per month. So those servers that you see, that's about a month's worth of processing, right? Those servers are delivered in 53-foot trucks filled with racks of servers. The good thing is the entire truck is filled with racks, so you don't even have to protect the racks or anything like that. They're just right next to, they're so close to each other that they don't even move in the truck, right? So it's nice and efficient from a logistics point of view. And a little shake, rattle, and roll, right? As Mark said, yeah, we can handle that. Right? We're going to throw it out anyway, a lot of it, right? And then this is what it looks like at the edges of that room, right? And I want to point out just that third photo there. So what that cardboard container there says, in a very thick cardboard, is it says net weight not to exceed 750 pounds. That container is 750 pounds worth of transceivers. So there are 700 pounds of little tiny lasers in that bin. And you don't know how many times I tried to convince the people, like, do you know how much you get, right? They're like, Eric, look at this. Look at how many there are. Like, this one's red, and this one's green, and this one's wide one, and a thin one. And I spent a weekend in this facility because of some unfortunate decisions that someone made at the end of a quarter. And so I took a couple hundred out, and I put them on a big piece of cardboard. And I'm like, look, guys, it's simple, right? These are wide, right? These are thin, right? These have the, you know, if it has BAD in Sharpie on, like, don't use that one, put that one back, right? And they're like, Eric, you don't understand. Like, this is 2 weeks worth of, right? And so the biggest problem in this processing and in these facilities is the sheer complexity writ large of everything that we've built, right? And trying to tease that out at the back end, right? And so that's what we did. Sorry, I had SW said I had to do a shout out. So I'm going to do a shout out to these sessions tomorrow. One of the reasons this can be done, right? Remember that when these racks come in, they still have their disk drives in them and their flash drives. These come from consumer companies, a lot of them, right, or corporations, wherever it is, but there's sensitive data on these drives. So the first thing that's done is the drives are removed, right? A lot of them have actually already been sanitized in the data centers by software, but nobody trusts that, so they're also crushed. Right? And so in the corner of this facility, there's a big crusher machine. Luckily, it wasn't working on the day that I interviewed, or else I might never have taken this job. 7 years at Seagate, and they're crushing them, right? But that's what we do. I also was supposed to shout out JM from Chia. He's been trying to work with the companies that force IT Renew to shred these drives. So if you can give, let JM tell you the story about why you shouldn't shred your drives and why it's safe. Go listen to Eric and the crew tomorrow about why it's safe to not shred your drives. Don't shred your drives. It's bad, right? So that's what that is, right? And then I'm not going to go into all of the economics, but so then basically with the economics of IT Renew, so IT Renew had relationships with many of the largest hyperscalers, right? And that's how it became to be, 50,000, 100,000 servers per month. And the goal of IT Renew was to put that material back into the supply chain, right? And so the way that we did that my team did that, is by building fully integrated racks. And we built racks of servers, storage, and networking. And our commitment to customers, our pitch to customers was, if we can use 85% or 90% material from that big warehouse that's otherwise going to go to e-waste, we can give you performance equivalent systems for 50% hard dollar savings at a minimum, right? And we were still paying for the guys who are taking it all apart and engineers and all that stuff, right? So at good margins, we were giving people 50% hard dollar savings compared to what they would do otherwise, with no compromise, right? And so how did we do this? by looking at the workloads of what was done. Oh, I'm sorry. So these are 5 racks. They're still running today in Dallas, Texas, right? This is OCP equipment. We did it with OCP equipment. There's a bunch of reasons for that. It's open, it's collaborative, right? There's good reasons, but it doesn't have to be, right? We happily lifted CPUs out of HP servers and put them into the fancy OCP servers. To Samsung's credit, right, we lifted DIMMs out of anything. DIMMs are completely interchangeable. With just a little bit of effort. Right? So what we were trying to do with all that is increase the operational phase, right? Keep the systems running longer, right? And the way we did it at IT Renew was we had a set of clients, folks who were sending us this equipment. The equipment was on average between 2.5 and 3.5 years old, sometimes older, sometimes a little bit newer. There's a lot of reasons. And so we were trying to facilitate this second use, right? Who's going to use the equipment for years 4 through 6, right? But it turns out that the trick is just to use the equipment longer, right? So you could just keep the equipment longer in its primary use and also get the same benefit, right? The role that IT Renew plays is simply to facilitate the second user of those components and potentially a third user. But the most important thing from an engineering perspective is all of these components, certainly at the component level, but even at the system level, are designed for 9 years, 10 years, 12 years, right? And those of you who have engineered these systems know that this is the case, right? Anyone who's ever worked at EMC knows that this is contractually possible, right? When we built those rack-based systems, even our object storage systems that were competing with the book guy, right? We committed a 10-year service life of those systems. And we committed our suppliers to a 10-year supply life, right? Yeah, the guys at Arista didn't want to support the same operating system on the same switch for 10 years, right? They wanted like 5 years, 7 years. Like, nope, it's written into the contract, right? So what do? They put a few more switches on the shelf. They have a few engineers who kind of pay more attention to the repos and so on. And it turns out there is no reason for any of the components at a lifetime level that they can't last 9 years at least, if not 10 or 12 years. So therefore, we can do this thing where we can, reduce the carbon footprint by increasing the operational life, and therefore amortizing all that upfront piece, and you can save cost. So this is a storage conference, so I brought you a worked example of some of the things we're able to do by just being a little bit creative with this extra constraint of if I can use a part that I already have tens of thousands of, then I'm better off than if I have to design something new. So I'm going to tell a disk story, right? So this is the drive enclosure we had. Again, we used OCP a lot, so this is kind of the in the time frame of the systems we were dealing with. This is something called a NOx enclosure. It's 30 drives in a 2U shelf, right? The server is separate from this, right? So it's a JBOD. The server is 1/3 of a U. Sorry, it's actually 2/3 of a U. There's a bunch of details I can talk about, but I made a storage example. So 2.3 U for 30 drives. And then customers constantly wanted us to compete with a 2U12 because a 2U12 is what's standard in the industry, right? So the good news is I can put 12 drives into my 30 drive enclosure and I can provide them what they want. It's just a little bit bigger for HDD. But then people wanted SSDs, right? And so if I do SSDs, okay, I can do it, right? So I can take my 3.5-inch slot and my SAS connector, SATA connector in the SAS backplane. I can put a 2.5-inch SSD drive onto it, right? It talks to the HBA that's in that server, right? It all works, right? It gives, for many CTQs, exactly maybe what people want. So I've now gone from 7,000 IOPS to 2 million IOPS by having SSD, by having flash instead of HDD, right? My watts per IOP is plummeted, right? Because I have this massive IOPS, right? My watts per terabyte isn't great, but maybe that's not what I was doing, right? I wasn't doing archive storage, right? But like, can we do something a bit better here? And so it turns out that we could, because since the time that that JBOD had been designed, right, the industry had evolved. Remember, all the drives are crushed before I get any of this equipment. So I have to buy new drives anyway. So why am I buying these SATA drives in these tiny little containers and putting them in the thing? Why don't I just get NVMe drives? And if I'm going to get NVMe drives, maybe I could even simplify that. I don't even need the case and all this thing, right? So I just use an M.2 drive. And so this thing is called an AVA board. It's a 4-drive by 16 PCI card. And it just brings 4 PCI lanes to each one of these 4 NVMe drives. No controller, no SATA, no SAS, no cables, no nothing. I'm just putting the flash chips right onto the bus with everything else, right? And we just heard how great an idea that was, right, in the previous presentation, right? And now, by also using higher density drives, I'm able to do, instead of the 29, I'm only able to do 25 terabytes. But then it turned out one of our engineers realized there was actually, on this back plane, we have a by 16 slot, and then we have a by 8 slot. And it turns out if you put, this thing is so simple, if I only light up 8 of these 16 lanes, then 2 of the drives light up, because it's not doing anything. There's no rewriting, there's no unpacking of the packets, right? All it's doing is passing the traces onto these drives. So as a result, we were able to put 6 of these NVMe drives directly on the by 24 lanes that we had. And now we have, again, a 24 terabyte instead of 29 terabyte. And again, I have 2.4 million IOPS. So if what the customer wanted was 2.4 million IOPS and 20 odd terabytes of capacity, I had now done it in 1/5 the space, right? And with so much less sheet metal, cables, et cetera, higher bandwidth, right? So I've used my kind of carbon footprint to simplify and optimize, right? And of course, since this is storage, you know, the zone guys are still here. If you want a lot of density, a lot of bytes, if you're doing archival storage, by all means, put 18 terabyte drives into this JBOD, and we did that as well, right? Now you're back down to 7,000 IOPS, ooh, sad, but you've got half a petabyte, right? And then, you know, in the same time frame, you know, the OCP project also created a larger JBOD, and now we're back to the JBOD where I was kind of 5 years earlier, right? Tombstone, put the drives in the JBOD, now there's 72 drives, 1.3 petabytes, right? And now that I've built out this entire table, you see, as you can appreciate as a storage audience, the complexity of what I've done, because there is an incredible dynamic range of performance and capacity characteristics, right? I have 2 million IOPS. I have a tenth, or what is that, 3/300ths of a watt per IOP in that NVMe system versus 37 watts if I'm running the HDD. But I also have, you know, the watts per terabyte, half a watt per terabyte up to 11 watts per terabyte, right? So sometimes, there's several times there's an order of magnitude. A couple of times there's 2 orders of magnitude in what you're doing with the system, right? And we're having the same components run across this entire gamut, right? And so if we can optimize for what the workload wants, then we can reduce and we can simplify. If we have to just accept the whole range of workloads, we end up with these in-between kind of solutions, right? And so it's kind of the engineering pitch here is that if we just look at the components we have, we can do much better. And this is what's going to lead in your data center, right? So, So then as a result, our mainstream offering to customers was 2 solutions. So if someone wanted flash, I gave them NVMe drives in the server. If they wanted more than 25 terabytes, I sold them 2 servers, right? If they wanted high density, then I gave them a JBOD with the Bryce Canyon, right? I actually noticed there's a talk here on the follow-on to this Bryce Canyon, the Grand Canyon design, you can listen to right after lunch, right? This applies not just in storage. Of course, I made a storage example. This applies also in memory, right? I can put a 64 gig DIMM into exactly the same slot that an 8 gig DIMM fits in. The power consumption is a little bit less than twice, right? And it's 8 times as much memory, right? What application doesn't run better with 8 times as much memory in the same system, right? Similarly with networking, we had, because of the way we were getting the materials, we had 25 gig by default. People be like, Eric, can I do cheaper if I do 10 gig? I'm like, if you want, you can plug in the 10 gig cable. Turns out it works. But I'm selling you a 25 gig NIC because that's what I have, right? I have 100,000 25 gig NICs, so that's what we're going to put in, right? And just in case you're like, oh, but what about AI and Moore's Law? So I have a little table here where I have 2 CPUs, two CPUs and then 4 GPUs. And the thing I want to point out is that 4th item down, that K80, right, a GPU from 2014 is still faster than any CPU at doing AI workloads. Right? So this is an AI score. There's a benchmarking kind of tool. So it rivals that Samsung Galaxy, right? Which is a great statement on something, right? But what's important is so that's your carbon footprint, right? So if you're doing AI processing, it makes sense to use that 9-year-old GPU and don't use like a latest Xeon whatever. It just doesn't make any sense, right? And we all know that, right? Just like you don't use CPUs to do Bitcoin, right? You buy an ASIC, right? But then the second part, remember the white part of my chart, is the cost, right? And so if you take the street price of that top GPU, the $3,600, and you spend it on the other stuff instead, then we can beat the much newer GPU on a dollars basis because I can get you into a K80 for $200, right? And if you take enough 280s to 18 of them to get that $3,600, then you have more than 100,000 of these AI operations. And by the way, this is being done to you on the cloud right now. Google will rent you a K80 on the cloud for $200 a month. I'll find you a $200 K80, and you can rent it to people for $200 a month and keep the money for yourself, right? I'm not slagging off the cloud providers in any way, right? The book guys, they're good, right? So carbon footprint, reduce the carbon footprint, increase the efficiency by focusing on the end user workload that you get for all of the carbon inputs. That will allow you to reduce the footprint of what you're doing or be much more performant or efficient, right? And it's also going to save you in cost, right? I have a lot of comparisons on the things, so I'm not going to go into all these details. I had to make one more shout out because SW told me I had to. So there's a BOF tonight on long-term storage, right? A lot of this was motivated yesterday. Christian from Cerabyte, kind of work with what you have. If you're gonna keep storage for 20, 30, 40 years, 50 years, a lot of what I said just magnifies itself out over time. And there were a number of sessions yesterday that looked at that, right? In the storage space, long-term storage is a great way to think about the carbon footprint of what you're doing. I'm not gonna tell you about Casaderos, and I'm not going to tell you about Freon, the Freon guys. So I'm going to thank you for listening, and I'm going to take 6 minutes. I'm going to take 6 minutes worth of questions. And I already sent it to Arnold. I'll update it with kind of the things, so you can read through. You can go read through about catadores. It's very very interesting in the motivation. You can cut through about the Freon guys. So there's a couple of guys that drive around in a truck and buy up Freon all over the country, and then they burn it up, and the state of California pays them millions of dollars to buy up Freon with cash and burn it up, right? So that's a story that's embedded in there. But I want to take some questions. So questions? Yes, sir. Yeah, so in fact we do that. I'm sorry. To repeat the question. That wasn't just the thing people do. It's because he says so. So the question was the componentry, right? So how do you separate the componentry in for example, a flash drive and put it back into different parts of the supply chain, right? So the bad news is that almost all the drives just go in a crusher and it all gets crushed together and then it's all just a big hunk of thing and nothing good happens. But it turns out that some enlightened clients are like, hey, there's some value, you know, we already scrubbed the drives or we had encryption to begin with. It's okay if you want to reuse it, right? And so what we do for some of those customers is we lift the flash chips off the board, right? So you have this controller board, right? Controller board is limited, right? Software is terrible. That's why you need software-enabled flash, because whatever's burned into that controller, right? So take away the board. Now you have the bare flash chips. You put the bare flash chips back into the thing, right? Now you've done you've done basically 100% or close to 100% of the economic value, and the scrap value, kind of the carbon value, maybe you've gotten to 80% and so on. Right? But my point exactly is if you think about how are we doing with all of that, it leads you to what is the efficient thing to do, right? How much energy does it take for me to lift the flash chips off, and so on, right? Similarly, if I want to reball the CPU, if I need to lift off, a socketed CPU is easy, right? You just unscrew the heatsink, take off the CPU, right? If it's soldered onto the board, I need to undo the solder. There's some cost to doing that, but we can calculate all that, right? Okay, what else? Yeah.
So you're taking old systems off the floor, putting them on the rack, redoing them. Those older systems come from a day when your computing power or storage density per kilowatt was a lot higher than the new stuff that's coming out. It's got more density per kilowatt, better CPU, core count per kilowatt. GPUs out of today. So that in the x86 world,
Yeah.
all right. Does your numbers take into account the fact
Yes.
that you have to use more power
Yes.
and more rack space and more cooling and environmental
Yes.
from that world?
Yes.
Do they take that into account?
Yes.
Not just scope 3, but that
So-
impact on your scope 2.
Yes, so we took that into account. So, I'm sorry, I have to repeat the question. So the processors, have different efficiencies, right? New processors are more, the word was a lot, but it's not a lot, but it doesn't matter. New processors are more efficient than old processors. Do we take that into account in our kind of scope 3 in our calculations? And so we do. So our positioning with customers was performance normalized 50% savings. So that means if the part that I was putting in was only a quarter as performant as the part that you were comparing against, I would sell it to you for 1/8 the cost of what you had. So on a cost basis, we normalized that out completely, right? On a carbon basis, it's a little bit unfair because basically anything that causes me to not send it to the landfill is good, right? So that means that I should lower my price to like an absolute minimum number just to get someone to use it and not send it to landfill, right? But if you just take that performance into account, we dealt with that, right? And it turns out there's very few components that with 3 or 4 years on them actually have any kind of 50% or 70% power reduction. It's usually 15 or 20%. And that's the critical point is if you use that carbon calculation and that end user CTQ, then you'll be able to follow the data on that and you'll always make a good decision. Right? You won't, by mistake, use an inefficient component to do something because you're taking all of the carbon into perspective, right? Okay, maybe, yeah, go ahead. Yeah.
So these systems fail more, so we have to more aggressively deal with reliability issues, with redundancy, and what is the calculus there?
Yeah, so do these systems fail more and does that need to be taken into account? And so it turns out now I've been doing this for way too long. And so I happen to know from lived experience of selling hundreds of thousands of disk drives, and disk drives are terrible, right? They spin, they're mechanical and all this stuff. The failure rates are so tiny, right? The failure rates in our experience at EMC, 80% of the failures that people called about were software problems. Right? They forgot their password, they weren't doing the REST API right, the IP address, they didn't have enough dots in the IP address, right? Of the remaining 20% that crossed my desk, oh, there's hardware problems. Eric, we got to replace these drives, whatever, right? 3/4 of those problems were just software problems masquerading as hardware problems, right? The number of hard drives that I replaced from a population of several 100,000 was tiny, right? And it was barely, almost imperceptibly worse at year 4 than it was at year 1, and that's hard drives, right? And so flash drives, very similar pieces, right? So the important thing is that the systems are maybe incrementally more failure, but it's a small percentage, and that means that the redundancy that we've put in, the erasure coding, all the conservatism that's built into it can take care of those failure rates, right? We found nothing where the failure rate goes from 1% AFR to 10% AFR because it's 5 or 6 years old, right? The only time we found it was this. We have a customer in Texas that runs their systems they open the garage doors of Texas and they let the dust of Texas through. And so their fans get clogged with dust. And so we replace the fans, right? So the important thing being that the amount of design and design conservatism and testing and so on that's built in gives such a wide margin that in practice, there's no difference at years 4 through 6 than there is at years 1 through 3. Right? Okay, I guess one final, I don't know who's in charge, but you're in charge. So he's taking me off. So I'm here all day. Feel free to talk to me. Feel free to find me online. So I'm kind of ER1P everywhere. It's an email address that was assigned to me years ago. But find me, and I'm happy to talk. Oh, right, and come to the BOF, right? Long-term storage BOF. Thanks, everybody.
All right, folks, we're on break until 1 when we'll be back into breakout sessions. So thank you again for attending the keynotes. Thank you. Great job. That was fun.